morning all participants and resource person. Today is the third day of our FDP program. And first speaker is Dr. Sunil Samantho, Assistant Professor of Department of Mathematics, Bankura University, West Bengal. So I request Dr. Samantho to start his speaking lecture. His topic stands for simulation of different mathematical models.
Okay. Thank you, Professor Das, for introducing me. I would like to thank the organizer for giving me the opportunity to deliver my talk. Today, I will discuss how we can use MATCON software to simulate any biological model based on system of ODs. Okay, let me share. Actually, I have no PPT. I will demonstrate only. Okay. What is MATCON? MATCON is a GUI software or package. That means graphical user interface. It is based on MATLAB platform, and without writing any explicit program, we can simulate biological models or system of ODs, and we can explore rich dynamics which cannot be captured in standard MATLAB. I will demonstrate how we can use MATCON to simulate simple models or any complex models. There are several steps to use the MATCON software. First, we have to load or import the model into MATCON software, and then we have to set the initial values and parameters, then we can compute. There are lots of steps in between for drawing one parameter bifurcation or two parameter bifurcation. Later on, one serious note is whenever we drawing the bifurcation diagram, if any biological feasibility um, does not hold, that means not biologically feasible, then we will discard that special point or that curve. Now I will start with logistic equation, how we can simulate this without writing program. Let me start the MATCON. This is MATCON. I have to run this one. It will give several small window. Here, this one is MATCON. So first I will select initial point. Sorry, I will load the system. Let us load a new system. That is, here I saw this logistic equation. So I will import the logistic equation into this. First I have to give the name logistic demo. No problem. What are the coordinates? Coordinates only 1, n. You can use any variable x, y, z, whatever. And the parameters are r and k. R is intrinsic growth rate and k is carrying capacity. Now we have to write down simply that n dash is equal to r into n into 1 minus n divides k. This done. Now we have to click OK. It will pre-compute the model, and now if we choose this initial point type, initial point, simple point, then it will give several window. Now we have to set the initial values and the parameter set. Let us choose the initial value 0.01 and parameter value 0.5 and this as 10. Now to draw the or simulate the system, I have to open a graphical window. Here we will see this. Here we will set in x-axis the time and in y-axis the variable n. After that we will set the time range. From this figure layout we can change the plotting region. Here we will choose the x-axis from 1 to 100. Now it is done. Now we have to click only the compute forward. It will give the result. The one more thing, the total simulation is based on this OD45. You can choose any other solver here, but we will choose here OD45, and here interval is given 100, or we can choose 500, whatever. Done. Sorry. Okay, now we can just compute forward, but it will give the solution. Now if we change the initial value and draw again, it will give another solution. Very simple one. So we can compute or obtain the time series solution very easily. Now if we increase this beyond carrying capacity, then we can observe the solution goes down and reaches to carrying capacity. So it is very simple. So we can compute any system and we can see the time series solution or phase diagram or bifurcation diagram. I will go step by step. Now I will show you the next one. Next example, I will choose the insect outbreak model. This is also one-dimensional system, insect outbreak model. Then let's check if we edit this system. Okay, let us edit this existing system. Then what we need to modify? We need to modify this minus n square divide 1 plus n square. This is done. I'm not changing the, okay, let's change the name. This is insect outbreak. Then we have to do the OK. Now again these pop-ups are coming. I have to set these points. Okay, no problem. Here again I will choose 0.01, r is equal to 0.5, and this is equal to 10. Now we will see little different dynamical result. If we compute check for initial value 0.01, it goes here. Now I can show something more, numerical window. In numerical window, it shows the simulation value. Here it is computing and the end value is this. Now if I gradually change or for different values, if I test for 1, it gives this solution. Now if I choose initial value 1.9, then again it gives this. But in insect outbreak model, if anyone read this already, there are two attractors. Now we will check if this is initial value has become 2.1, then we will observe that solution trajectory goes to another attractor. This is 7.3 approximately, and so on. For this system, we will show the one parameter bifurcation diagram, and we will show why these two attractors are coming. Okay, so for this I will choose the initial point whenever this PO, that means this orbit last point, will be considered as the initial point. I'm choosing this one. What's the problem? Something is okay. Okay, let's choose initial point again. I don't know, something is error is occurring. Okay, I am terminating. I will start again. Okay, let's run. Okay. Point type. Woody window. Okay, now I will change the variables here. In x-axis, I will choose coordinate, sorry, not coordinate, parameter r. With respect to r, I will draw the one parameter bifurcation and set the region in, therefore the region will be, let's 0.4, sorry, not 0.4, here 0.4 to 0.7. Okay, and coordinate is 0 to 12. My version is little older, 6.11, maybe that's why it is giving some problems. Okay, now I have to choose the initial point as the last point. Again, it is not working. It will be okay. Let me compute once again. It is already chosen. I don't know why it is not working. Okay, let me try once more. I am opening once, here it is opening two times. I don't know. Graphical window, what's happening? Select image. I don't know what is happening here. Okay, let's move on. This point as equilibrium. Let me restart the MATLAB itself. Sorry for the interruption. Don't know what is happening here. Okay, let me start again. The problem is it will take little bit time to initiate the MATLAB. I can explain here in advance. For insect outbreak model, if we choose this parameter set r is equal to 0.5 and k is equal to 10 and simulate with these initial points, we will attain this type of figures. I already demonstrated it. Now, if I choose any one equilibrium point, this end value, and then compute the one parameter bifurcation with respect to R, then it will show like this. Now I will demonstrate. If everything is okay, then I can show this picture. Okay. Here initial value is already assigned. Now I will just compute forward. Okay, let's start. No. Stop here. I have to select this point as equilibrium point. No, I don't know what's wrong is going on, but it is not working. Okay, let me explain here. If we set this equilibrium point as the initial point and draw this one parameter bifurcation diagram, we observe that from starting from point 5, it goes for forward curve, it will be here, and for backward curve, it will close to this, and here 1 BP occur. Now let me explain what LP means. LP means the saddle node bifurcation. That means the system will have two saddle node bifurcation at this point. This is R1 0.383971. Here one saddle node bifurcation occurs. That means when the growth rate is increasing, then suddenly two new equilibrium appear in the system. Again, if we go increase R gradually, then we observe for here R2 is equal to 0.559525. Here two equilibrium point suddenly disappear from the system. That means saddle node bifurcation occurs. Here in this particular region, from R is equal to R1 to R is equal to R2, in this region the system will have three non-negative equilibrium: N1, N2 and N3. Interestingly, this from LP to LP, between this equilibrium bunch is unstable. N2 is unstable, and on the other hand, N1, the first equilibrium point will be stable and third equilibrium point will be stable. Therefore, in this region, node-node bistability occurs here. Here, it is also very popular in the terminology hysteresis. Here, we observe that if the initial value is above this branch, consider point 2 from here, for R is equal to 0.5, if initial value is chosen 2, then it will go to N3, that is very high density. Now, if we decrease the initial value, that is 1.9, then it will decrease to the N1. It settle down to N1. This is called hysteresis. If we are not changing the parameter values, but we are changing the initial value, and the system converges to other attractor. Okay. Now I will try to demonstrate. I don't know, today the MATLAB is not working properly according to me. So now I will demonstrate how we can compute Rosenwick-McCartan model. So I will not start any new MATLAB window. I will window the open previous model. In last two example, I edited new program, but I have one program already loaded. To reduce the time, I will choose them. RM model. Let us choose this one. I don't know. It is very unfortunate. Nothing is working. Our model, let's edit it. Okay, we computed. Let's see whether it works or not. No, I don't know what is happening here. Only one. Very pathetic situation. Another mat count is opening. Okay, let's try from it. Okay, I am sorry. This is right now my mat count software is not working. So I am just try to explain in my Word file whatever it is done here. So similarly, if we incorporate this system like here, what we, I'm very sorry. Here we select the system editor load, this one. If we plug in this system, the RM model, two-dimensional system, where prey grows logistically and prey functional response and it decays linearly. Now, if we plug in this system, then we observe this type of situation. If we, I am here, I don't have picture for phase diagram and time series solution. Just I have drawn the one parameter bifurcation. First, we have to select these initial values and then we will compute, and for a is equal to 0.55 we obtain a stable interior equilibrium, and if we increase this a value then the system will give oscillation. Now for drawing one parameter bifurcation diagram, we need one interior equilibrium, stable equilibrium. So first we set this parameter set and then compute and get the stable equilibrium point. Then we choose that stable equilibrium point as the new initial point, and then in 2D window we will set in x-axis A and in y-axis N. Then we forward the computation and it will give like this. Here one hop bifurcation will occur, and whenever we started from 0.55. So whenever we go compute backward, it gives one branch point BP. That means here one transcritical bifurcation occur. So again, if we choose this BP as the new initial point and continue BP EP curve, then we obtain this equilibrium branch. This is nothing but the axial equilibrium where K is 10, that is this is fixed, and in this branch the Pareto population, that is P, is 0. So left hand side of this branch point, the axial equilibrium point is stable and interior equilibrium is unstable. In the right hand side of this BP point, the interior equilibrium point will be stable. This is the stable branch, and axial equilibrium point will be unstable. Now we also observe one hop point here, and if we continue considering hop point as the initial point and continue hop limit cycle, I am unable to show this choosing hop. If we choose curve type, this limit cycle, this is not okay. Now it has changed. I don't know whether it will work again. Oh, it is working now. Okay, if we choose this hop point and curve type limit cycle, but here it is not changing. Okay, leave it. Then we can compute hop LC curves. This will give this type of. Now, interestingly, this hop is supercritical. If we observe here in MATCON main MATLAB window, the special points, all special points will be here in command window. We have to collect them, and here I have collected. H is occur at A is equal to 0.571429, and the corresponding interior equilibrium point is this. This is N value, this is P value, and this is the bifurcating parameter. And the first Lyapunov coefficient is negative. Therefore, the limit cycle hop bifurcation is supercritical, and the limit cycle are stable. This limit cycle is stable. Now, there is a technique to draw the only upper curve and lower curve without filling this region. If we use this technique, I am unable, very sorry, I am unable to demonstrate this right now. We can draw this type of picture. Only maximum point and minimum point we can select this one using simple click. Now, if we want to draw the two parameter bifurcation, then from here we have to choose the select points. What points? Here all the branch point, equilibrium branch, from equilibrium branch, this EP1 and EP2, we have to choose branch point, and then again we have to choose hub point. Then in two parameter space we have to set the window 2D space. In x-axis we choose A, and y-axis we choose K. Then choosing the branch point as the initial point, and let us check here. It is not properly shown. Still I am no. Don't know. It is totally messed up. Then we compute forward and backward. We will get this transcritical curve. And again, if we choose the hop point and extend the curve for hop, here it is chosen hop, and again we choose the curve type hop. Then the curve will be hop. This hop curve gives this one. Then this whole region is divided into three distinct regions. In this left hand side, beyond left hand side of the transcritical curve, there are only axial equilibrium point is stable. In this region between these two curves, the interior equilibrium is stable, and in the right hand side of the hop curve, the limit cycle oscillation present. Now if we edit with color, then it looks like this one. Okay, so very sorry I am not able to demonstrate anything. My system is not working, particularly MATCON is not working properly. I just in 2 to 3 minutes I will give another example. Again, if we consider an equiepidemiological system with alley effect, which looks like this. Here this term refers as the alley term. This is predation driven alley, and this term is disease term. Now if we incorporate this system and set these parameter values and initial value, and we draw the one parameter bifurcation diagram, then we will obtain in EP curve there are two hop point and one BP point. Two LP curve, LP point will be obtained, and one BP point is obtained. Considering this BP, if we again continue BP curve, then it will give this another hop in XY plane. Here jet population is extinct and another BP. Now if we check, the first one is equilibrium curve, EP1 curve. It starting from here, it gives one BP, one hop, second hop, third hop. This is saddle node bifurcation, LP, again BP. And choosing this BP, if we continue, it gives another BP, and in backward computation, it gives another hop, which is predator free hop in XY plane, and it touches this BP and goes on. Now, if we divide this region according to the special point, it gives like this. There are seven distinct regions with seven different dynamics, and there are lots of bistability, tristability, and here this node bistability, node oscillation, node cycle bistability, tristability, etc. in different regions. And if we draw the two parameter bifurcation considering beta and theta as the bifurcation parameter, then we will observe this type of two parameter bifurcation diagram, and all the regions are described here. In region 1, the bistability occurs where all species extinction and predator free oscillation, sorry, not susceptible only equilibrium point, and there are lots of rich dynamics. Now I am almost at the end of the lecture. I would like to discuss the advantage and disadvantage. The advantage is I don't have to write any MATLAB code to simulate such complex model. It will give a lots of dynamics in this MATCON platform, and we will miss one thing, the chaos. We cannot draw the traditional bifurcation diagram or cannot detect chaos in bifurcation diagram, but we can detect chaos through phase diagram or time series solution using this MATCON. Okay, thank you. And again, I am very sorry that I cannot demonstrate due to some technical glitch. Thank you.
Hello, sir.
Yes.
Sir, you have shown that in Rosenzweig-McArthur model to plot maximum and minimum values of limit cycle, sir. How to plot that, sir?
How to plot? Okay, let's
just
only
at
show.
least tell me.
Okay. I'm trying to show this how, just mechanically. First, I have imported the system as RM model. So I have to go there from MATCON platform. I have to go systems here. What happened? Yeah, these systems. Again, I am showing this systems folder. I have to go there. Okay. In system folder, I will obtain this folder corresponding RM model. This is RM model. Okay. Then here we will see diagram. In diagram, I have to I have all the curves here.
Huh.
Okay, this is HLC curve. If I load this HLC, the from hop point to limit cycle continuation, and one more thing we need, hop curve maximum minimum. This is a very small 4 to 5 line program. We have to open it. This only 4 line program. It will plot the maximum point and minimum point. Now I have already loaded this HLC curve, and now if I compute this hop, this one, it will give this. Now I have to, okay, let's check whether I can show this one or not. Lots of error is occurring, no problem. Now in editing mode, I will have to go in editing mode. Now if I choose this one, okay, uppercut, and simply paste here, it gives this one. And if I choose lower one and click here and paste here, it gives only this. Now clear?
Ah, yes, sir.
Okay, so you have to, this is not inbuilt. If you require, you email me, I will send this 4 line program, or you can take the snapshot.
Sir.
Here n is 2 because I have 2 dimensional system. If you have 3 dimensional, then you have to modify it accordingly. Okay.
Ah. Sir, I have one more question, sir.
Yes, yes, please.
Sir, how to initialize and continue homoclinic orbits, sir?
Oh no, I don't have that level of depth. I don't know. I did not use this one.
Uh-huh. Okay. Okay, sir.
You can
Thanks.
you can follow some tutorial. If you
Ah,
require, I can send you
ah,
for MatCon. There are 6 to 7 PDF is available. You can also search in Google. Then you can try that one.
sir. Thank you, sir.
Thank you, Dr. Samantu. Thank you so much for your nice input.
Thanks.
I request Dr. Samantu to stop your presentation. I request Dr. Samantu to stop your presenting. Okay, thank you. Our next speaker is Dr. Kushal Kumar Srivastava. Sir, are you available to speak?
Yes, hello. Good morning, everyone.
Okay. Thank you, sir. Good morning. And Dr. Srivastava is the Associate Professor of Department of Mathematics, IIT Patna, and title of the lecture is A Novel Multivariate Function for Spencer Series Modeling. So I request Dr. Srivastava to
So, am I audible? Okay. So first of all, good morning, everyone. I would like to thank organizer, especially Dr. Krishna Pada Das, for his kind invitation and allowing me to share my work with you. As you can see, I hope the slides are visible. Click here to return to video call. Okay, very well. So can you please confirm the visibility of the slides? All right. Okay. Thank you. Great. So as you can see, this work is basically a collaborative work with Dr. Tanuja Das, who is currently postdoctoral fellow at University of New Brunswick, Canada. The first icon here, which is the QR code, if you are interested, this is linked to the paper which was published in Chaos, Solitaire and Fractals. And it has also won the J.B. Shukla Award recently in IMS 2023. So if you are interested, you can read this paper here. I'll try to go briefly about the work which is done in this paper. Dr. Das, I guess I have 30 minutes, right? Sorry? 40 minutes, okay, fine. So as the title suggests, what we are doing here in this work is that we are trying to consider a novel incidence rate function for infectious disease modeling. So many of us must have seen there are various kind of incidence rate functions which usually describe how the new infections are generated when the disease is spread. So the outline of this talk is to highlight the significant factors which influence the incidence rate functions, because that is what we want to explore. We further would review certain literature which is related only to the incidence rate functions, and what are the findings corresponding to those incidence rate functions, or what are the most important findings which are corresponding to those incidence rate functions. We'll try to consider a more comprehensive and a realistic incidence rate functions which will incorporate or which will inherit the important properties for the incidence rate when a disease spreads. And we'll try to establish the relation between the properties of the incidence rate function and the pattern of the disease spread. Before moving forward, this is a very nice quote which many of us might have heard, that all models are wrong, but some are useful. The practical question is, how wrong do they have to be not useful? So what is the sense of having this line here is that we don't claim that this particular incidence rate function is the perfect one. This is under certain assumptions. This will follow certain diseases, but it cannot be blindly applied to every disease. I guess there is some noise from somewhere, so kindly mute yourself. That will be helpful for me. Thank you. So the point here, which I'm trying to make, is that we cannot blindly incorporate an incidence rate function everywhere. There are certain disease patterns, and we have to follow. If those disease patterns are followed, then a particular incidence rate function should be used. Having said that, we'll discuss about what the incidence rate function is. It basically describes the rate at which the new cases occur when there is a spread of disease in a population. And this incidence rate function mathematically can take different forms depending on the underlying biological and social factors. By social factors, we mean even the behavioral response of the individual. So some of those factors are mentioned here. The first among them is the biology of the disease, that is how the disease transmits from one individual to the other individual. So if it is a contagious disease which spreads from human to human or individual to individual, then there will be a different kind of incidence rate functions. If it is not contagious and it can only be spread via some route, then there will be different kind of incidence rate function, and so on and so forth. The function also depends on the incubation period, virulence, and other factors which are associated with that particular disease. And therefore, one function doesn't fit all. That's what happens. It also takes care of the population characteristics. For example, one among them that how individuals react to the available information regarding the presence of the disease. We all have seen that during COVID time, since there was severity of the disease, there was no treatment available. So people tried to avoid the contact with people, the other people, and that led to reduced number of contacts, eventually leading to reduced number of contacts with the infected individuals, and which eventually led to a reduction in the number of new infections. So such population behavior as a whole impact a lot, and that is one of the point or one of the major concern for our modeling, for our work, this particular work in today's talk. Environmental factors such as climate, weather, pollution, those also affect this incidence rate functions, because some diseases they usually spread during certain weather conditions. Then the interventions and public health measures such as vaccination campaigns, quarantine measures, contact tracing, behavioral, social distancing, or what you can call is that say any kind of restriction imposed by the government or those organizations, they also affect the incidence rate, and therefore the number of new individuals they change. So this is a typical diagram. Here, if you see in the left side of the diagram, people are mixing and then they are getting infected. The red individuals are infected. This is shown in the right side of the diagram, where S, the blue color individuals, are represented as the susceptible individuals. Some of you might be aware the susceptible individuals are those individuals which are prone to the infection. They can get infected if they come in contact with the infected individuals. These red color individuals are represented by the infected individuals, and when they come in contact with the healthy individuals, they infect the healthy individuals, and in the upper side, if you see, there are the individuals. So there is a mix of individuals. So they mix in the population, and then they become infected. So the spread of infection is via infected individuals to the healthy individuals when they come in contact with the infected individuals. If there is no control, if there is no information, nothing, people keep on having the similar behavior as they were having earlier, then usually we say that this is mass action, and we model it, the expression in the terms of S multiplied by I, which means that as many as infected individuals are there, they will be proportionally infecting the healthy individuals. However, it has been observed that that's not the case in the real life, because when there is a disease spread, people tend to change their behavior. They take precautionary measures so that the spread of the disease is not as fast as usually should be expected as the mass action type. So what happens is that there is something referred as the force of infection, and that force of infection is usually dependent on the factor which we refer as information, and which we are representing as a parameter m. So if people are informed, then less number of infections will occur in comparison to the regular infection. So which means that the population's behavior affects the rate of infection, and which eventually can be modeled in terms of this incidence rate function, which is referred here as capital F of SI, which is also dependent on another parameter m, which is measure of the information. Information regarding the disease, how when a disease is spread, there also spreads the information regarding the disease. So depending on the information, this force of infection, this is modified, and the property of this function FIM is that FIM is less than I, which means that whatever function you choose for all I, it should be bounded below by I. And another factor which should affect is the information. So del F over del M should be negative. Okay. So if we incorporate these two ideas, why del F over del M should be negative? Because if the information increases, definitely the function should be the decreasing function. Larger the information, smaller should be the incidence. That's what the idea should be. So keeping that in mind, there had been several such functions. Certain examples are mentioned here. There are many other functions as well. So this is a popular function which in ecology you call it as Halling type 2, and then the other one is Halling type 3. So here we refer it as a saturated function, both of them as saturated function, monotonic saturated functions, and then certain other functions which are having the behavior which is non-monotonic. So we have plotted here these functions. So for example, the first function where the force of infection is proportional, I mean straightforward, just I. That is the very first thing which I mentioned here. If you see, it is a linear function, which is a linear force of infection, which leads to bilinear incidence rate. Bilinear means both S and I having the linear, so the bilinear term is appearing there. This is the popular fundamental model, which is referred as Kermack and McKendrick model. So there we consider the incidence rate as beta Si. So if you see the infection rate is actually proportional to the I, and this Fi is a linear function, blue colored function. We'll keep on comparing our other functions with these blue colored functions. So in the second graph, if you see here, here in the down, Fi is I over 1 plus Mi. Look at this blue color. This is our linear relationship, which is in the first graph. The blue color is the linear relationship, and the other two graphs are plotted for the increasing value of m. M is equals to 1 and m is equals to 2 for these values of I. So these are the graphs of Fi versus I. What is Fi here? Fi is the force of infection, which you mentioned here, and obviously Fi is less than I. So when we plot these graphs, we look at that as the parameter related to the information, as m increases, this function Fi basically decreases. So red color is for m is equals to 1, and black color is for m is equals to 2. So this has its impact on the dynamics of the disease. When you consider SIR model, you will see that with the increasing m, which is the level of information, the proportion of the recovered individuals grows. So more recovered individuals will appear if you are modeling a SIR model. You can see that if you plot the time series, you will realize that the recovered individual grows as time increases with the increase of m information. Then we consider the second one, which was considered by the Ruan and Wang. In this case also, this blue is referred to this baseline, which is Fi is equals to I. and the function fi is I square over 1 plus mi square. And here also we have plotted two cases for m is equals to 1 and m is equals to 2. Obviously, m is equals to 1. I mean, as m increases, this reduces, the fi reduces. Moreover, if you notice, there is a behavioral change here. It keeps on growing smoothly and it saturates. However, here there is a slower growth in the beginning and then faster growth at the towards the later period and then before saturation. So what are the impact here is that this factor m, the information related factor m, reduces the possibility of the disease spread as the endemic equilibrium disappears when m increases. So for the larger value of m, the certain endemic equilibria they disappear. So this, because of the presence of the information, there is a chance that the disease might get eliminated. In the third case, which is considered by Xia and Ruan, if you see these two, I mean, fi is equals to I upon 1 plus mi, this is monotonically increasing. Fi is equals to I square upon 1 plus mi square. This is also increasing and saturated. So these are increasing and saturated functions. But in this case, this is not monotonically increasing. This function is increasing first and then decreasing before going down. So in this case, the behavior is similar. Larger the m, smaller will be fi, because that's the thing which we mentioned here. The del f over del m is actually less than 0. So if you increase the m, then del f over f will be decreasing function as m. So if you consider a model with this kind of incidence rate function, then you can find out that there will appear the half bifurcation. What do we mean by half bifurcation is that periodic oscillations will appear in the population. So oscillatory behavior can be observed from the endemic equilibria. There can be oscillatory behavior, which there can be oscillatory solutions which will be appearing there as you have a certain critical value is obtained. Such work one can see in the references section, which I will show in the end. So this one is a work which we have also found that there are various nonlinear properties which one can see. So we have also considered a model with this incidence rate. Further, there are a couple of more functions which have similar typical behavior as the one proposed by Lu. Is that here in this case, what happens that the critical value of m, the information parameter, decides whether the disease will die out or persist, or there will be oscillatory solutions via half bifurcation. And similar behavior are also observed in case of the function which is chosen by this Lu and others in 6. So having this kind of information a priori, we thought of, because if you notice here, there are two important behaviors noted by these functions. One is that in the case of I square upon 1 plus I square or I upon 1 plus I, the infection increases as infective population increases, and later on it saturates. So that means that there is a kind of constant infection rate after a large number of infective. However, in cases of these functions which are by Xia and Ruan, or these functions which are by Lu and others, you will see that initial phase the infection is spread. So they for certain diseases it is true. When the disease spreads initially, there is no control available, no treatment, no vaccination, nothing. But later on, when those controls are available, you can apply them, and therefore it is reasonable to consider that instead of saturating, this rate of infection will actually be on the decreasing time. And this makes reasonable to believe that the infection rates might not always be monotonic. They can be non-monotonic. So So these are certain observations which are mentioned here, is that either Fi decreases and tends to 0 or Fi saturates. Biologically, how this saturation appears is because of the crowding effect. More individuals are there, then there is no chance of infection to spread to others individuals, because it's a kind of, it will provide a kind of shield to the healthy individuals. On the other hand, the other functions, they can be considered as that they keep on reducing due to the inhibitory effect. Okay, the people's behavior, the available control measures, and so on and so forth. So these are the two important observations which we have from these functions, and we kept ourselves, motivated to proceed for another novel function. When we have the thought that we should propose an incidence rate function which is related to the various factors of the disease as well as population, and therefore a generalized incidence rate function which addresses, as I mentioned, a monotonic, non-monotonic, as well as saturation behavior under different circumstances. So, of course, the same function cannot be both monotonic and non-monotonic. So we wanted to see that the function at different times should behave as monotonic as well as non-monotonic, and should eventually show the saturation behavior. So with that in mind, we proposed this generalized incidence rate function, which, if you can see, is the linear combination of the function of I upon 1 plus mi square, which is non-monotonic, and I upon 1 plus mi, which is monotonic. So it's a linear combination of these two functions. But it's not just the linear combination, but it's because of the presence of both kind of influences in the disease. This function has a very peculiar behavior, which we have shown here. So one thing to observe here is that these epsilon1 m1 and epsilon2 m2 are relevant constant. Usually we refer them as inhibitory parameters, m1 and m2 as inhibitory parameters, or sometimes they also referred as saturation parameters. So if you notice carefully, when this particular condition is satisfied, epsilon2 upon m2 square is less than epsilon1 upon m1. Then the proposed function initially grows. Okay, proposed function in the sense of force of infection. So this proposed function initially grows, it reaches it to its maximum, then it starts decreasing, and eventually it becomes very small and saturates. So if you think from the biological point of view, in the initial phase, infection spreads. Later on, the inhibitory effect come into play, which are the characteristics of the population. So they start playing their role, and therefore people tend to change their behavior, and therefore the infection, the force of infection decreases. And eventually what happens that due to the crowding effect which is there, this saturates to a number. So this non-monotonic and saturated behavior, this can be seen and this can be observed in various diseases which are there, and therefore this is one of the important incidence rate functions which can play a crucial role. However, if you choose this kind of parametric condition, or if your model shows this kind of parametric condition, epsilon2 upon m2 square rather than epsilon1 upon m1, then f initially grows monotonically, then decreases, and then there is a minima here, if you see. And so before getting saturated, it further increases and then saturates. So this is something which is very interesting, which we have observed, that we have not seen any other function which is behaving in this manner. Okay. So this is important, that sometimes the disease might, the force of infection might dip and then again start increasing, and eventually it may settle. So it goes to maximum, goes to minimum, and then again goes up and then settles there. So these are the two behaviors which are shown by the functions which we have considered. Now, considering with this incidence rate, we have this very simple SIR type model where two aspects are considered. One is the force of infection, which is influenced by the available information, which is leading to either the crowding effect or the saturation in the model. And another factor which we are considered here is this treatment. So this treatment is also considered to be having a non-linear effect. The reason being that whenever there is infection spreading in a population, you cannot provide treatment to every individual. So if you cannot provide treatment to every individual, then the removal rate should not be proportional to the infective population. Rather, it should saturate to somewhere. In other words, there is always a limitation of the medical resources, and therefore, if few individuals are getting treatment, those which are equal to the number of available resources, the other individuals, if they come and they want the treatment, they have to wait until and unless the resources are available. So that can be modeled via this expression I upon 1 plus mu(i). So simply we consider this function here, these two functions here. One is beta SFI and other one is alpha I upon 1 plus mu(i). So these are the parameters which are mentioned here. I guess those who are working in this area, they might be aware. We have considered the constant inflow rate. D is the natural death rate. Delta is the disease-related death rate, and alpha is the treatment rate, and mu is the treatment saturation constant. With this, we find that there is a biological feasible reason. As you know, these are the populations, so we must have biological feasible reason. So it's bounded biological feasible reason. And the basic reproduction number, which gives you the measure that how many secondary infections are possible from one infected individual. So we observe the basic reproduction number is this for our model. We also observe that there are certain equilibrium. One among them is the disease-free, and other one is endemic. So obviously, we want to go to the disease-free equilibrium, but even if in certain cases it is not possible, we want to go to the endemic equilibria where the I population is the minimal population, which can be even if it is going to some endemic equilibria, it should have, if it is a very lower in endemic, lower range endemic, then also it's fine. So as you can see that the I equation is a 4th degree polynomial. So there is a possibility of maximum 4 endemic equilibria. And we have put here the set of all those endemic equilibria, the conditions here. So when R0 is less than 1, you can see the maximum possibility of 4 endemic equilibria. And when R0 is bigger than 1, there is a possibility of maximum 3 endemic equilibria. And these are the sign of the coefficient which should be there. And these coefficients are mentioned here in this expression on the right side. Hi is the expression which represents this polynomial. So it's not easy to solve this polynomial, and therefore we go using the Rauth-Hurwitz criteria. We see that how many roots are possible. Some of the examples I have shown here. So the cases when you find the 2 endemic equilibria or even multiple 4 endemic equilibria when R0 is less than 1, we refer those cases as backward bifurcation. Okay. And when there are 3 endemic equilibria when R0 is bigger than 1, this leads to some interesting dynamics. So the characteristic equation at E0 is referred as P0. One can easily see that if R0 is less than 1, then this is locally asymptotically stable, that that disease free is locally asymptotically stable, and it is unstable if R0 is bigger than 1. So one can easily see from the characteristic equation. However, for the endemic equilibria, the characteristic equation turns out to be this quadratic equation, and there are various cases. So the cases are, so we have mentioned these equilibria in this sense. So if there are two equilibria for R0 bigger than 1, if there are two equilibria for R0 bigger than 1, we have put them in this ordering. The larger one we will call, larger one for I we will call as I21, and which should be larger than I22. If there are three, then we'll call them I31, 32, and 33. This ordering is considered. That means the equilibria corresponding to I21 will be referred as E21, and corresponding to I22 referred as E22. So this is how we have considered them. Okay. So these are the cases of endemic equilibria which are mentioned here. As we mentioned, the endemic equilibria are possible if R0 is less than 1 or R0 is bigger than 1. So one in equilibria is possible only if R0 is bigger than 1. Two are possible only if R0 is less than 1. Three are possible only if R0 is bigger than 1. And four are possible only if R0 is less than 1. So these cases basically refer to that. That's why this even star mentions that R0 must be bigger than 1. And in that case, this one is stable. So you will have transcritical bifurcation. In other cases, those equilibria are mentioned, that what kind of properties they will possess, whether they will be stable or unstable, that can be seen from this table. So this is collection of all the behaviors of these. So I will show you a few graphs where you can see that how some of these equilibria are mentioned. Not all graphs are presented here. If you are interested, you should check the paper. So these are the bifurcation analysis. As we have a lot of results there, so we have not put everything here. These are the bifurcation results. So even at the even, we find the backward bifurcation. When this condition is satisfied, mu TC is this relationship of the parameter. You can see this is a bigger relationship of the parameter. At beta is equals to beta star. Beta star refers to the set of parameters when R is equals to R0 is equals to 1. So corresponding to that, beta is equal to beta star. We have found this value. When mu is smaller than mu transcritical, we find that there is a transcritical bifurcation. Some of you who are aware about the backward bifurcation and transcritical bifurcation in epidemiology, this is referred as transcritical. So one no endemic equilibria to one endemic equilibria as R0 becomes larger than 1. In case of backward bifurcation, there are two endemic equilibria if R0 is less than 1, and one endemic equilibria if R0 is bigger than 1. And then there is a saddle node bifurcation, which appears at the beginning of the backward bifurcation. Then there is a half bifurcation, which appears at beta is equals to beta h, where beta h is given here. I think I missed it. Yeah, so probably I missed the beta h. So provided these conditions hold, then at that beta is equals to beta h, you will get the half bifurcation. If you notice, we have a quadratic equation, and therefore the coefficient of lambda is 0, and constant term is bigger than 0. That's how it becomes like, you know, you will have a purely imaginary root in this case when you have the characteristic equation. So there are certain observations which we saw numerically, that if epsilon1 increases, the possibility of backward bifurcation increases, and if M2 increases, then the possibility of the transcritical bifurcation increases. Saddle node bifurcation may occur when the derivative of f is bigger than 0, but for sure it does not occur when the derivative of f is f with respect to I is less than 0. Half bifurcation occurs when f prime is bigger than 0, but does not occur when f prime is less than 0. So since I told you this is a non-monotonic function, so the behavior of the function will be like increasing side and then decreasing side. So this saddle node and half bifurcation occur only on the increasing side of the function, not on the decreasing side of the function. Okay. So we have observed certain threshold values as mentioned E1 start, which is a stable equilibrium. Cross beta is equals to this beta critical parameter. Then you will start getting the oscillatory behavior with the endemic equilibrium becoming unstable, and further endemic equilibrium becoming stable again with another half here. Okay, so we refer these values at the point of forward half and the backward half. And if you see, the behavior for E1 goes via the sequence of stable to unstable to stable. So stable, then unstable, then further stable. This is how the equilibria will be. For a particular value of beta, we have plotted the time series so that we can show that. So this particular value beta is equals to 0.0021. This lies in this range where the E1 star is stable. Beta is equals to 0025 lies in the range. You can see that there is already a closed orbit which is drawn in blue color. And when beta is equals to 0.0035, it lies in this stable region. So one stable solution trajectory, then oscillatory solution trajectory, and then another stable solution trajectory. These are the time series plot for different values of betas. This is another interesting plot which we have plotted for the case of having multiple equilibria. Okay, so in this case, if you see, this blue line is R0 equals to 1 line, and there are multiple equilibria which exist. So as R0 is larger than 1, there are 3 equilibria. When R0 is less than 1, there are 2 equilibria, endemic equilibria. By equilibria, I mean endemic equilibria. So as R0 crosses the line R0 equals to 1, the 3 endemic equilibria exist, out of which in this band, you will see that the green represents the stable and magenta represents the unstable. So the first initially the equilibrium E33 is stable. This is the ordering I already mentioned. E31 is larger than E32 is larger than E33. So E33 is stable, and then it moves from stable to unstable. Then it remains unstable. The second equilibrium remains unstable. And during that period when the second equilibrium is unstable, the third equilibrium is actually stable. Okay. And this the disease-free equilibrium, that is stable if R0 is less than 1 and unstable if R0 is bigger than 1. So this graph mentions the multiple existence of multiple equilibrium near R0 equals to 1, and it shows the stability properties of those equilibria. What is interesting here is the behavior of the disease. If you notice, if your initial condition starts in this region, which are near to E33 and R01, the disease will actually get attracted to the lower endemic equilibria. However, if your initial conditions are starting somewhere here, then you will get attracted to the upper endemic equilibria. So this shows that there is a possibility of different level of disease eventually with time, uh, which is dependent on the initial population, or which is dependent on that how that infection was initially there present in the population. So uh, various endemic possibilities may appear according to this result when there is a disease which is at different initial levels, which is in the population. So this is the conclusion here. As I mentioned, if you can see reason 1, because here f prime is bigger than 0, and in reason 2, here f prime is less than 0. So in reason 1, half may occur, and in reason 1, saddle node may occur, but in reason 2, neither half nor saddle node occurs, which I have already mentioned. So this is one information which we have got from this model. We further extended this model to this delay model, where we introduced the incubation delay. This is the time taken by the infective individual to become infectious, and we consider we consider this the similar calculation for this model. The endemic the number of endemic equilibria does not change with the introduction of delay. Only their stability properties change. So we find that there is the characteristic equation which is available here, and the characteristic equation for the endemic equilibria that is available here. So there are certain conditions. So for the critical value of tau, where the half bifurcation may occur. So we see that from the bottom line, if you can see from here, the number of purely imaginary root of the characteristic equation, provided the conditions. These are the conditions. C5 is this condition, C6 is this condition, C7 is this condition. So if these conditions hold, so for example, if C5 holds, then there will be no purely imaginary root. Okay. So the behavior will remain the same for all delay tau. There will be one purely imaginary root if C6 is satisfied, which means that the oscillatory solution will exist via half bifurcation as delay crosses the critical value of the delay. There will be two purely imaginary roots as multiple oscillations will appear, and corresponding to that we find the sequence of the delay parameters, which I will show in our next slide. So depending on the various conditions, the characteristic equation shows the existence of 0, 1, or 2 purely imaginary roots, depending on the conditions which we have mentioned here as C5, C6, and C7. So we have collected the values of those critical parameters of delay, and we are referring them as half R1 in the R. H stands for half, R stands for the region, so HR1, HR2, HR3. Similarly, we have used some abbreviations here. One can see SR1, so stable region, and UR1, unstable region, 1, 2, etc. They mention the regions. So we have found the value of critical value of delays, and wherever the half is appearing, we call them as HR1s, etc. R1, R2, R3, and then whenever there is the solutions are stable, we call that range as stable range, and the rest of the range as unstable range. So for example, I mean, you can see them in the graph. Probably it will be easy for you to see, but this is how we have, in order to mention that precisely. So we have observed that the supercritical half bifurcation appears at tau SB H is equals to these values of tau critical, and the supercritical half appears at these values of tau critical. We also observe that there is a half of bifurcation in two parameter space, beta and tau, for beta HS and tau HH. This we will show numerically, and there are certain other conditions which shows the existence of sequence of half bifurcations. Say, for example, if C8 is satisfied along with C1, then you will have only stable equilibria. If C9 is satisfied, these are the conditions, C8, C9, which are mentioned here. Then we will have a stability switch. One half bifurcation point will appear. So we will get from stable to unstable, and then it will remain unstable forever. So you will get, the typical half bifurcation case. If C9 is satisfied, then you will get the two values of the delay. One where the half bifurcation appears from stable to unstable, and another one where the half bifurcation appears from unstable to stable one. And then a sequence of half bifurcations will be appeared till you become unstable. So depending on the parameters, multiple half bifurcation switches will appear from stable to unstable to again stable to so on and so forth, and finally unstable. So the end result will be unstable. Then furthermore, in the similar manner, we have also found that there is a possibility of sequence from unstable to stable and then finally unstable. We'll show you these graphs in the numerically. So this is one single stability switch when the endemic equilibrium was unstable, and then finally it becomes stable. This is the time series plot. So it's a backward bifurcation, unstable to stable. This is another sequence important result where usually we see the half bifurcation results from stable to unstable to stable and then so on and so forth. Here we have also seen, apart from that sequence of stable to unstable, we have also seen the sequence of half bifurcation from unstable to stable to unstable to again stable and then so on and so forth. And finally, this becoming as unstable. This is the two parameter bifurcation plot, which refers the tau as a function of beta. We have plotted here the tau curves and the points at which they intersect. At those points, you will find that double periodic oscillations exist. So this is the last curve here, which is mentioned here. So basically, this results mention that in this particular result, the plot A mentions that in the tau beta parameter space, there are different regions where you will get different kind of behaviors. Okay, and those different behaviors are mentioned here in these figures. In this case, you are moving to the stable even star. In this case, there is a periodic oscillation. So the even star is unstable and a periodic oscillation exists around this point. With even star is unstable. In this case, not only one periodic oscillation, but there is another periodic oscillation which exists around that point. So there is double periodic oscillations which appear. Okay, so we refer it as half bifurcation. This is the coexistence of different frequency oscillations. The pink one, you can see this is the pink one, and the blue one, this is the blue one. So this is the three-dimensional graph, and even is unstable in this case. So with this, we come to the conclusion. I guess this is what my time was. We come to the conclusion that as the parameters vary, so a lot of information is here on this slide, which is as the conclusion of all the information which I have already discussed, which I have already discussed in my previous slides. Therefore, I am not repeating it again. So this is the summary that this monotonic behavior, non-monotonic behavior, and saturated properties are shown by this proposed incidence rate function. And there are certain properties which are shown as the parameters are varied, and these parameters have various non-linear effect on the dynamics of the disease, which shows very rich and complex dynamics. What we could not do in this is that we could not find the normal form of the coding to bifurcations, which we think that can be one of the future directions. One can look at those coding to bifurcations and their normal forms and explicitly find out the forms of those bifurcations. We can explore the saturation property. I mean, if one is interested, one can also do that, explore the effect of the saturation property on the incidence rate function on the disease dynamics. So this is it. If there are any questions, I will be happy to take them. So thank you. Okay, all right then. Yes, thank you very much. So should I stop presenting? So I hope this must have interested to some of you. So if you are further interested, you can look at that. Interested in slide, many times I get the request. Those who are interested in slide, I will put it in the chat box. You can copy it from there. You can find the slides at this link. Yeah, so the link is appearing on your chat box now. You can copy the link. You can find the full slides there. And if you're interested, you can read the paper as well. Thank you. So may I disconnect now? Yeah, okay. Thank you very much.
Yeah, I'm audible. Yeah, thank you, Dr. Das. So I'm sharing my screen. Yeah, is the screen visible to all of you? Okay, thank you. So thank you, Professor Das, for inviting me for the faculty development program on the recent trends in biomathematics and dynamical system with bifurcation, chaos, and simulation methods. In this talk, I would like to discuss that how we can find the solution to the ordinary differential equations, because here to find the technique to get stability or finding exact solution or using of some iterative techniques, there are many methods through which we can discuss the solution to the differential equations. Because whenever we are discussing a mathematical model, we are creating some differential equations, ordinary or the partial differential equations will be there. So in this talk, I am give a basic talk on how we can talk about the existence and the uniqueness of solution to those differential equations. And this is my topic is there. So here, most of the real world problems encountered in the field of a science, engineering, and decision making may be expressed as a mathematical equations, serving as the fundamental building blocks for creating comprehensive mathematical model. And mathematical modeling is a rapidly developing branch of science that focuses on developing solutions, predicting behavior, and analyzing the events of a real world problems. The mathematical models come in various forms, encompassing it's having a linearity, nonlinearity, static characteristics, dynamic characteristics, determinism, or stochasticity. And these models are frequently represented through the differential or integral equations. So, to understand and be able to apply the three principles in modeling any phenomena with the differential equations, we can say that discovering the differential equation or equations that best describe the specified physical situation. So means first of all we have to be create a model with the help of a differential equations that describe it specifically. And second question in our mind will come up, if the model is being defined up, we have to be find either exactly or approximately the appropriate solution of the equation or system of equations. So we have to be interpret the solution in terms of a phenomena. So that will be, we have to be understand. So for this, the existence and the uniqueness of a solution to the first order differential equation given a set of initial conditions is the one of the most fundamental results of the ordinary differential equations. And to understand that a differential equation is an equation relating a function to one or more of its derivatives, that an initial value problem is a differential equation. This is a dx by dt is a function of a dx. So we have some questions in our mind when we are discussing some differential equation or differential functional equation. So what is the condition for the existence of a solution for an initial value problem? How does one know if an initial problem has a unique solution? And for what values, for what intervals does the solution to an initial value problem exist? So these some questions will be in our mind while dealing with the differential equations. So the existence and uniqueness of a solution for a differential equation is useful for finding applications, maybe in a physics, biology, or economics. The fundamentally important question of the existence and uniqueness of a solution for the initial value problem was the first answered by the Lipschitz in 1876. And then in 1886, Peano discovered the initial value problem has a solution if the function f is continuous. Then in 1890, Peano extended this theorem for the system of first order ordinary differential equation using the method of successive approximation. And then Picard and Lindorf presented existence and uniqueness theorem for the solution of initial value problem. So here in the today's talk, I'm discussing some of the techniques here through which we can discuss those methods. The first of a question that in our mind is about the existence of the solution out there. And the existence of a solution, the existence theorem will be given by the Picard. We say that if the function f is continuous in a rectangle, this region that contains the point, then the initial value problem defined by this equation has at least a solution in a subinterval which contains the point x naught. So here we talk about in the theorem number 1, we have talked about the existence result for the initial value problem. And what is the condition should to be added on this theorem such that we can talk about the uniqueness result? So further they added up the one more condition here is that if the function f and its derivative respect to be x are continuous functions in the region that contains the point t naught x naught, then the initial value problem given by this equation has a unique solution in the subinterval which contains the point x naught. So we'll discuss up here about the Picard's iteration scheme here. If the function f and its derivative respect to bx are continuous function in rectangle R, then there is a sub-interval H lies between a T and A in which there exists a unique solution for the initial value problem given by this equation number 1. So motivation to get the solution we have, suppose there is a function x that satisfies the initial value problem number 1, and integrating it out we can get a solution. So ut from t0 to t f of s us ds is a solution which is equivalent to the equation number 1 is there. So now we show a solution to the integral equation using a method of a successive approximation or Picard iteration method with an initial condition u0. By taking up a u0 is equal to be 0, we can go with the find the u1 by applying in the equation number 2. So we get the u1 is equal to be integral 0 to t f of s u0 s ds. Similarly, you can go with the u2 and so on. We can calculate the un plus 1, which is the integral from t0 to t f of s uns ds is there. Now, this Picard iteration generates a sequence. So to prove the theorem, we have to be satisfied some of the conditions. We have to be satisfied, we have to be check it out whether the sequence that we talked about exists. If the sequence exists, whether that sequence converges, and does it satisfy the integral equation, and is that the only solution we have talked about, such that you can say that whether the solution is being unique. So say for example, I can choose any arbitrary differential equation here, say initial value problem, I'm considering it out, dx by dt is equal to be some function which is equal to 2 times t into 1 plus x with the initial condition that the x of 0 is equal to be 0. Say that we will apply the method of successive approximation. And we suppose that here the u1 t is equal to be 0 to t by applying up the condition here. Just we have already said that the ut is equal to be a function of s into the us is there. So by applying up here, so we get that 0 to t 2s into the 1 plus u0 s ds, and substituting the u0 is equal to be 0, you can find the value of a u1 as a t square, as a polynomial of a t square out there. Then we can go with the u2t. Again, successive approximation is going to be applied up. And again, we can find out this is equal to be t square plus t4 by 2. This is the not the u0, this is the u1. By putting up the value of a successive approximation. This is the 2s into the 1 plus u1 of as, which is equal to be, by integrating it out, by substituting the value of a u1t here, in the second equation, we can get this is the t square plus t4 by 2. And so on, we can calculate the u1t, which is equal to be t square plus t4 by 2 factorial plus so on. So by mathematical induction, we assume that this result is true for n is equal to be k. And we have to show that this is true for n k plus 1. So the limit exists if the series converges, or this limit u and t exist. So it is very easy to be check it out using up the ratio test. We found that this converges to be 0. So we get that the given series converges for all t, and since this is a Taylor series, so it can be integrated and differentiated in its interval of the convergence. Thus, it is a solution of the given integral equation. And note that if we can see up the series ut is equal to be e power, this is an exponential series of a e power t square minus 1, which can be shown to satisfy the given initial value problem. We found that the ut, whatever we have a solution out there, the existence out there, it is equal to be e power t square minus 1. Now, whether this solution is unique, suppose that there are two solutions ut and the vt satisfies the given integral equation. And we have to be verify that this ut is equal to be vt or not. So we can check it out, ut minus the vt. So this is equal to be 0 to t 2 times s us minus the vs. And taking up the absolute values and restricting the t from 0 to a by 2, where a is any arbitrary, we found that this modulus of a ut minus vt is less than equal to be a times 0 to t us minus the vs ds out there. And let here the ut is equal to be integral 0 to t us minus vs. This term we have taken up as the ut. Then it is easy to verify that u of 0 is equal to 0 and u of t is greater than equal to 0 for every t greater than equal to 0. So it is, we can say that the ut is a differentiable, and the differentiation of a ut with respect to t is equal to be the ut minus the vt modulus. So we can say the u dash t minus this term is the ut. So u dash t, by substituting in this the given inequality, we found that u dash t minus the a times ut is less than equal to be 0 for any t lies between a 0 to a by 2. And by multiplying it with the e power minus at, we found that the differentiation of this term is less than equal to be 0, or we can say that the ut is less than equal to be 0 with arbitrary a. So we found that here we said the ut is greater than equal to 0 and this is ut is less than equal to 0. It is only possible when the ut is equal to be 0. And what is the ut? So ut, we can say that ut is equal to be 0 implies that this ut is equal to be the vt out there for every t. So we get the existence of the sequence solution, and then we have talked about the uniqueness of a solution. So we're not going to be proof the result of existence and uniqueness, but with the help of that, this example, we have justified that the solution exists and is being unique out there with the help of a series. So if you go like to the proof of this existence and uniqueness theorem, the first condition is there, we have to be restrict to this time interval, and then we have to be put up some conditions that the f is continuous in the given rectangular region, the function f should be bounded, and we have to be choose the h, and then by induction using a Picard iteration scheme, we can prove that this u and t is less than equal to be empty out there. And second step, we have to be show the sequence convergence. In the convergence of a sequence, we have to be get the continuity of this derivative of the function with respect to bx, and we have to be choose the Lipschitz constant, and then considering up that the un t minus the un minus 1t, the difference between this sequences elements we have is less than equal to be this term, which establishes the convergence of a Picard iteration scheme. And in the third step, we have to show that the convergent sequence converges to the solution of the initial value problem. And that we have to be choose of the iteration scheme in terms of integral equation, like here 0 to t f of s uns by using a successive approximation technique, and take up the limit un plus 1, which converges to be ut. We already checked it out, and is equal to be limit and converges to be infinity of this function. And using up a uniform convergence of a Picard iteration scheme, we found that ut is equal to be this. And using up a continuity of the function, we can say that the ut, this function is being converging to the ut out there. So it is easy to see the uniqueness of this by using a contradiction and assuming two solutions. So this is the way we get the solution. The solution exists and unique to the initial value problem. So here we found that using up this Picard iteration scheme, or using up this existence and initial value problem, the question is why we need the restriction of this interval of taking up this h. The second, what is the significance of the conditions that this f and its partial derivative, its derivative with respect to bx, being continuous in the rectangular region? So whenever we have to talk about the existence and uniqueness solution, just I said that here we have to be go with the restriction of this interval, and then we have to be talk about the conditions that the f and its derivative are being continuous. Why we need of this? What is the significance for this? So we can say that in the next examples we can try to be elaborate that part. So consider the initial value problem. We have x dash is equal to be a x square and x of a 0 is equal to be a 1. And here if you can say that the function here we have is the x square and the partial derivative is 2x, and which are continuous in the rectangular region we have. And solution, if you go with the any technique to get the solution of this, like a variable separable method, we can get up the answer to that. This problem is xt is equal to be a 1 over 1 minus t. And if you can check it out, this is undefined at the t is equal to be 1. So you can say that the interval of existence should be verified with the interval of a continuity for the given function. Similarly, if you can say that, consider the differential equation x dash is equal to be x power 2 by 3 and x of a 0 is equal to be 0. Here the function is equal to be x power 2 by 3. It's continuous in any rectangular region centered at the point 0, 0. But if we go with the derivative with respect to bx, this is not continuous in the region near 0, 0. So solution to the initial value problem is 2 by 3 to t power 3 over 27, which satisfies the initial problem. And it is also see that x of t is equal to be 0 is also a solution. So the solution is not unique. So here we said that the condition that we have added up, that the partial derivative is continuous in the uniqueness case out there. And if it is not continuous, in that case, we can say that the solution is not unique. So this is the first system that is being described by the Picard to get the existence and uniqueness solution out there. And then this scheme is being extended by the Banach to get up a solution. Some of the conditions are being modified. He said that now he used the contraction operator. And he said that every contraction in a complete metric space has a unique fixed point. So the contraction, you can say that here, if xt is a metric space and t is a self-mapping from x to x, then t is said to be a contraction if there exists a alpha lies between 0 and 1 such that this condition is being satisfying. And these are some of the examples for the contraction. So here, you can say that every contraction mapping on a metric space is uniformly continuous. So whatever the condition that we have already implied on the operator, which we set up in this differential equation, that this f and this partial derivative are being continuous. So we have considered up in the case of this condition that contraction mapping is continuous. So under that Banach hypothesis contraction theorem, we can say that the iterate scheme xn plus 1 is equal to be txn with the arbitrary x naught belongs to be x converges to the unique fixed point x of a t. And here we can calculate the error estimates are the prior estimates we have, which is the dxm comma x is less than equal to be alpha power m over 1 minus alpha d of x naught comma x. And the posterior estimates, so here equation number 3 represents the bound can be used at the beginning of a calculation for estimating the number of steps necessary for obtaining a given accuracy. And number 4 is the posterior bound that can be used at the intermediate stages to check whether we are possibly converging faster than the suggested equation number 3. So we see that the two successive iterations xm and xm plus 1 are nearly equal, and then it guarantees a fixed point. So using up the Banach contraction theorem, we can also talk about the existence and uniqueness result of the initial value problem, which is quite being necessary complicated over the R and taking up the more conditions we have to be verified using a Picard iteration scheme. But here we have to be verified only about, we have to be check it out that our structure in which we are taking it out, it should be complete, and the operator that we have taken up is contraction, satisfying the contraction condition, and then we can talk about it has a solution, and that solution is also unique. So say that we have this problem number 5, and the function here we have assumed to be continuous function satisfying this Lipschitz continuity. And then the given initial value problem number 5 can be reformulated as an integral equation, and then it considered as a operator. This t of a ut is equal to b u naught, t naught to t, f of s, u s ds is there. And then if you can consider up that, suppose that this function is continuous function and Lipschitz continuity at the point u out there, then there is a unique continuously differentiable function that satisfies the equation number 5 out there. So we see the proof. It's simple to get the proof out there. So only we have to show that this t is a contraction on the space of a continuous functions defined on this time interval under the supremum metric. So we have this d of a tu, tv is satisfying of this condition, and we can say that here this satisfies the L times delta into d of a uv. Now if this L delta is less than 1, then t is a contraction on this interval set of continuous functions over the interval t naught to t naught plus delta, and therefore there is a unique solution. So we found the unique solution only by getting up some of the conditions to be justified by the Picard iteration scheme to the using of a Banach's contraction principle. And then similarly we can use this method to get up a second order differential equation, can also be checked it out with the boundary value conditions out there. We have this condition, say problem number 8 is being considered it out, and by choosing up the condition over the g is function is continuous and satisfying up this condition, and choosing the Green's function by calculating the Green's function here in this interval, and we can take up the space as a set of all continuous real valued functions over the interval I and take up the supremum metric. It is easy to show that this xt is a complete, and the only thing is again we have to be verified that this operator is having a contraction mapping is being satisfied. So if you say that this operator is being written as the equation number 9 is being represented by the f of xt, which is equal to be 0 to 1 g of a ts, g of x comma xx ds is there, and we can say that for any x and y belongs to be a space of a continuous real functions over the interval I, and we can get that this is 0 to 1 integral gts into this. We can found that this is satisfying the contraction condition, and hence by the Banach contraction principle you can say that this f has a fixed point. So ultimately I would like to conclude that here using up this simple technique we can iterate sequences through which we can find up a solution to a given nonlinear problem. Or we can also check up the stability of the results using up a Picard iteration scheme or using up the Banach contraction principle out there. So thank you. If you have some query, you can ask me up in that case. Yeah. Yeah, this is just an introductory talk in which the candidates is being just who has started up the study about the differential equations would like to be get up the solutions to those equations. We can get up by using up these iterative schemes, and even there are many other iterative schemes through which we can talk about the solutions to those problems. Thank you.
Yes, sir. Good afternoon, sir. Ah, yes, sir. Sure, sir. Thank you. Is it visible, sir? Yeah. So, hello everyone. I'm Dr. Indrajit Kumar. I'm working in Central University of South Bihar, Department of Statistics. And today I'm going to give some brief introduction, a brief lecture related to statistical computing and analysis with R. Actually, this software is very popular these days, like not in statistics only, in mathematics and all allied area related to statistical computing. Whatever the process, whatever the research work we are doing, we have to produce either the real data analysis or we have to produce the simulated result based on the model, whatever model we have developed, like in mathematics, whatever model we are developing, that time we need to supply some validation of that model. So that model can be validated by with the help of simulated data, and for which the R programming or R software are very helpful for generating the simulated sample from the based on the model, and we can supply the we can validate that to develop model in our research work. Okay, so little like this software is very popular. Initially, it was started in 1996 by Ross and Robert, and they started. It is the updation of S plus software. It was previously name was S plus, and then after that its names called R language or R software. Basically, our software provide some high quality visualization of data these days, data science, machine learning, artificial intelligence. These are the area on which we have to produce some visualization of data, or we can make some inferences, and we can extract the data like data mining. So from the data, what information hidden inside the data, we have to extract from there. So that time a statistical software R can help to produce some good information from that data. Okay, so basically there are two for installing the software, we need to require either R or R Studio. Actually, R Studio providing good interface to do any statistical computing. Good interface means there are some flexibility in R Studio. We can make project type related. Project means we can do some documentation also. We can make a web page also based on the based on the statistical computing. Whatever the analysis we are doing, that analysis we can make HTML file, or we can make any Shiny. R Shiny is one web portal. On that web portal, we can supply our whatever the analysis we have done, that analysis we can display on website. So R software for running in our computer or our PC, we need to install R, and then we have to install R Studio. R only is enough to do some basic computation in a statistical computation. But if you want to do good, or you want to make any website, or you can you will get more number of features in R Studio. In that R Studio itself, you can work like Python script will be provided. Okay. So some basic, I just want to show which type of interface of R Studio and R softwares are there. Let me show you. Like this, when you install R software, you will get this icon R, whatever the this is the R software, and here this is called console, and here whatever code we have to write, that we need to open a new script. In that new script, whatever the suppose there are several database available in R. Okay, so several data sets available. I just want to show you, you can drag it, you can put anywhere. Okay, so here this is known as R script. In that R script, we can write down our code, and this is console. This is known as R console, where the output of that code will come. Okay, so suppose, for example, here I'm writing one database I want to extract, one database I want to show from the R software itself. There are so many data sets available in R. I just want to show you one data set, its name is Longly. Its name is Longly. Just write down Longly and just press Ctrl R. The data set will appear in console. Okay, and if you want to see that data set in a table form, so just write down VIEW, view command, and just write down the data set name. This is the command, and just run it, Ctrl R. So this is variables are written here. This is the table. This is one column, one variable name, second, third, fourth. So these are the year and just I want to know which data set, details of that data set I want to know. So just you write down question mark and write down the name of that data set. It will give just run it. Ctrl R. So this will gives you the help. Okay, just put question mark and write down the data set. Whatever the help you want to know from the R about the data set, about any packages, you just write down the question mark and run it. Okay, it will appear one window. That window will show you what are the information related to that package or data set. So here the information given Longly data set, and these are the information over there, you can know whatever the variable name and what basic information you will get. Okay, so just I want to show you what is R. So this is called this software is R. Okay, and similarly here we are writing in R script, and I just want to show you R Studio. So interface of R Studio interface of R Studio will be like this. Okay, there will be four window. Okay, one window, this first window is top left, is known as R script. Here we can write the data, here we can write the code. Okay, so similar way, there in R Studio we have to open R script. Here the script window is already given, and here the left down, it will be R console, and the right top, it is environment. You can get like environment, whatever the work you are doing, history, and the connection tutorial. Some example will be given here. Okay, packages, whatever you are doing, so that information. And here you will get option to like import the data. Like data, there are several format we can like import the data based on like SAS data, SPSS, Excel, text, whatever. Many features of data we can import. Okay, and in this, in the fourth right bottom, here it will display like visualization of data. Suppose I want this longly data I want to plot. So just I want to plot this longly data. Here run command is there. So you just click on run. Here it will appear the like outcomes of that plot, or basically plots, and plots will appear here in the fourth column. Okay, fourth window. So this is the just a scatter plot between the variables. So many plots you can make, like there are box plot, whatever the plots you want to make, just write down the data name inside the function. This is the box plot. Okay, so here 1 2 3 4 5 6 7 variables are there, and their box plot. Okay, so this is the interface of R Studio and R software. Okay, okay, so next some basics of R, like we can use it as a calculator, and we can use at calculator whatever the work we are doing in calculator. So this is the like whatever we are doing, we can use like calculator. Okay, and creating vector, basically in R what we have to do, like for writing any vector means like X is a variable. Suppose height of the student, so 15 students heights are there, so that height, like that variable vector, we have to write down C, and in this bracket we have to use like a comma among the observation. Okay, so and this vector, suppose we are applying any function, we can directly apply, and here we apply the log function. So log of X coming here. Okay, and like we have to write down log of base 10, base 2, whatever base we have to define, here we have to supply. Okay, and anti-log like exponential of X, so these are the anti-logs value coming over there. Okay, and then we have to apply like exponential of log of X, it will come original number. Okay, so similarly, like mean, median, mode, standard deviation, quartile. Okay, so like we have to first define the X value, or we have to define the data, whatever the data we are having, we have to define, or we have to import the data from the Excel sheet, and like Excel sheet or some text, whatever format we are using, from that format we have to import the data in R. Okay, and then we have to apply like mean of X, this is coming like this is the value, and for which the mean of this coming this one, mean of Y, standard deviation like a median, quartile, and these are all are the value. We have to apply the probability, like we want to know like first quartile, second quartile, and third quartile. We will get like this much number. Okay. Minimum. So so many functions are given in R, like whatever we are thinking, like just what will be the R code for length. So just you start writing just in R Studio. Suppose X is a variable, X is equal to C. We want to write down some number, suppose 4, 8, 9, 10, 41, 6, 36, whatever the value we have defined here, just run it. And just I want to know the length. So just len, suggestion will come. Okay. In R Studio, whatever the work we are doing, like suppose I don't know the R code for mean. So just you just write down mean. It will come. Okay. So mean of X, just here you write down. It is very easy. Like when we are using R Studio, you just write down 3 keywords and suggestion will appear. Suppose like I want to write down median. So median. So see the median command here coming. So whatever the work, whatever code, if we don't know, just write down 3 keywords similar to that name, like English word. So suggestion will come. Like sometime it is coming problem, like whatever the work we are doing, that time we don't know the which functions are available in R and which type of code we have to write down. Okay, so median of X, like whatever the work, this is a statistical computation, and okay. So like length of X we have calculated, and here in which in this R software we can define our own function. Our own function means suppose some functions are not available in R, that time we have to define our own function. And this is like this function and this option is very much required in our research work. Sometimes the whatever the model we have developed, that model functions are not available in R. That time we have to define our own function, so that we have to do the computation part. Okay, so basically this part is mostly useful for our research work. Okay, in R Studio, and also if we know the good, if we are having good command in making the like functions, that function we can supply to the R community, like our package we can submit to the R. Okay, R community, like we can help them. It is open access software, so many researchers has given their own function, like their own defined function, whatever suppose we have developed one function, that function you can like give to the R community. Okay, so here we can define the function name, like whatever the function we are defining, the code coming function. Okay, and function in which form, like functions of X, functions of parameter, functions of what we have to supply. So this function of X, a standard deviation divided by like a square root of length of X. So this is we have supplied. And suppose X is a data, so just we need to supply the X value here. We will getting the like whatever the function, a standard error for the X. Okay, so any function here, the coefficient of variation, one function we define here, coefficient of variation. So that time like X we already define over, like X is a data we already define in R, and the mean of X, and like this we have to supply. Okay, so we can create our own function. Suppose here whatever what this is, they have given height, they have this function in height is what, this much. Okay, different height they have given, and they want to know the standard error. So just SEM is a function, whatever we have defined, and just SEM and height variable name we have to write inside, and that will give like this is the standard error. Okay. Similarly, coefficient of variation for height. So this is the height. We have to find out coefficient of variation. So coefficient of variation, just CV function name and the variable name we have to supply. Okay. So it will appear like coefficient of variation is this one. Okay. And there are several features given in R, like we can make different types of plots. So this is the bar plot. We can make box plot, bar plot, any type of line plot, histogram. Okay. So based on the data, we can make like parabola, we can plot, integration, we can plot. Okay. So several things we can plot in R. We need to have the data and okay, numerical value we have to supply the numerical value, and this R studio and R can be used to find out the integration as well, like integration, derivative, whatever, like basically people are doing in mathematics. Mathematica is one software like that. Mostly work we can do in R also. Okay, so like we can define the vector for the categorical variable. We can supply the category like male, female, or their like height, whatever the value corresponding male, females we can supply. So this is the factor command by which we can supply the male, female factor. Like here, this is the observation for which we are applying female, male, and like we are doing the labeling. Okay. And we can create the vector also, like this already previously, and the whatever the value we have supplied, either it is good, bad. So like it is category, we have to define the category. So I just want to show you one data set, like VIEW. This is iris data set. Okay, so you just run it. So when we run this iris data set, okay, so in R it is available iris data set. Basically it is related to a species. There are 3 types of a species. So I just want to show you the correspond this a species, like it is category. There are 3 species available in this data set, and these species related to flowers color and like sepal length, petal width, sepal length. These are the related to this data is related to flower. Okay, availability of like a species in flowers. Okay, so like a category, I just I have shown the category, like corresponding category where. Okay, corresponding category I have shown in data set. Okay, so like we can find out the correlation, we can find out regression, whatever the statistical method we have to like a statistical analysis or any model we have to develop. So that time we can use covariance we can find out, like correlation we have to find out, variance we have to find out. So that time we just need to supply the small function. Covariance means COV, correlation means COR. So there will be like X and Y we need to supply, and for which we have to find out the correlation. So similarly, scatter plot, we can find out like we have to plot X and Y so that we can get clear picture whether there is any correlation or not. So this will give the correlated plot. And this is LM command. LM means linear model. So this is linear regression will come. Okay. So this syntax we have to use for applying the linear model, linear regression. Like here it is simple linear regression. Only two variables are there. It may be multiple variable in the x side. So we can just write down x1 variable x1 plus x2 plus x3, whatever the variables names are there, just we need to add on plus plus plus. Okay. So like for this regression line, we have plotted the regression plot. Here it is the regression plot based on the given data points, like sample we have taken x and y. So this is the fitted value of that regression, like x and y. So this is the regression line. Coefficient is this one and this one. Okay, so this plot we got. So like I just want to, there are several colors we can, like this plot we need to this point we can change the color, and some other colors we can check. So here suppose x we have taken 20 values, y we have taken 20 values, and here pitch means like different type of shape or colors we have to supply. Colors we have taken 20 colors, and this is pitch means there are different format of plotting. So in the next slide you can see this is the 20 observation, each observation having different values. Suppose this value is 1, so this is denoted by this rounded 2. So like this different values having different shapes we have provided. So like for the visualization purpose, we can supply these things. Okay, so we can use the creation of matrix. In that matrix, like we can have so many variables and like numerical values that matrix will come. And for that matrix, we can apply, we can same use the matrix operation, whatever the mathematics we are doing. Same things we have to done. Just here we need to, like for multiplication, we have to check whether which command we have to use to multiply two matrices, and which command to find out determinant. Like determinant, just det, it will come determinant. So this is x1 and x2, two variables, and I just want to combine, like make a matrix. So this will come like C bind. C bind means column wise. Okay, and R bind, it will come row wise. So like binding of this variable, it is coming column wise, and binding of this variable, it is coming row wise. And matrix operation, like this symbols is used to multiply, and this is used to transpose, and this is used to determinant, and this is used to find the inverse of that matrix. It is very easy. Okay, so many things we have done in this slide. Okay, basic operations we have done. Like we can create list, we can create data frame, and like creation of data frames, like data frame, in that we can supply quantitative, qualitative, all types of data variables we can write down. Okay, so many things are there. We can use so many things as statistical computation, like if we are facing some non-linear problem like Newton-Raphson method. So packages are there in R software, like NLM, you can use optim function. Many functions are there. So like this is the parabola we can plot. So several plot functions are there. We can make the different kinds of plots. Okay, and these days basically we need to like supply a student some software, like we can recommend them to like learn, even they are belonging to mathematics, they have to learn these things. Like R and R Studio is very good for everyone. Like it is related to multidisciplinary. These days this software is very popular. So many things we can do, like in data science, this type of packages we are using, like ggplots. Slide is quite more, so like we are sorting of time. So if you are having any questions, you can ask. These things are there. So many things are there. Just you need to explore these things. Thank you. Hi. Okay, thank you. Anyone having any questions or like query in future? If you just want to like contact me, you can contact me for any help. Like this is my email ID. Like for doing any work or anything. Okay. Thank you, sir.
Yeah, good afternoon. So I think I'm good. Hello, am I audible? Okay. Okay, so can I present? Okay. So basically today we are discussing about one ecological model. Basically this is from the eco-epidemic model, and this is two-way non-predator model. And here the model basically is developed for the effective control of pest population. So the main terms here are like pest and its impulsive control. So pest basically nothing. This is an insect population and which is dangerous for the crops population. So we know every year a large amount of the crops is consumed by the pest population. So this control is necessary. And impulsive control means there are lots of control methods available in the literature. So like you can see here, like chemical control, microbial control, biological control, cultural, and many more. So here the cultural and the mechanical control method are the very traditional method, and these methods basically require lots of time and lots of effort. And nowadays the peoples are mainly interested in either the chemical control or in the biological control. So in chemical control, we basically release the pesticides, chemical pesticides, and these chemical pesticides can attack on the pest population, and it can kill a large portion of the pest population. But due to the chemicals, basically other environmental also polluted, and even the natural enemies. Natural enemies means another insect which can consume the pest population. So that natural enemy basically is the friend of the farmers. So due to this chemical pesticides, natural enemies can also kill. So sometimes the chemical control method is not fruitful for our society in terms of the economic, ecological balance, in terms of the like environmental pollution. So in that case, we have to actually search an alternative method for the chemical control. So here, the biological control is the alternative form of the chemical, where in place of the chemical, we release the other insect population, and that insect population can attack on the pest population. So here we release the natural enemies population, and moreover, we can also release the infected pest population. Because when the susceptible pest population got into contact of infected, so the susceptible becomes infected, and it can increase the mortality of the pest population. So here there are basically two methods in the biological control. One is the releasing of the natural enemies, and other is the releasing of the infected pest population. So in biological control, we use two methods, and here we also use chemical control because there are lots of chemical available in the market, like imidacloprid and other and these chemicals are less harmful for the environment, but these chemicals are very specific. So here we try to control the pest population with the help of less use of the chemical and mainly focus on the biological control method. And you know, these control methods cannot be applied continuously. So here we release the chemical or the natural enemies in a fixed moment of the time. And that's why to form it or to develop the mathematical model, here we use the impulsive differential equation. So this is basically impulsive differential equation system, and it is the combination of two type of equation, the continuous and as well as the differential equation. The continuous means dx over dt. So here the behavior of the state variable x can be given at a except at a specific point, and other than that point, or we can say at a particular point, the behavior can be given by the discrete condition. So basically, impulsive differential equation is nothing. This is the combination of the continuous and the difference system. And here to develop the model, we use this previous impulsive differential equation. So the first model is a prey-dependent consumptions to prey one predator eco-epidemic model concerning the biological and chemical control at different pulses. There are lots of literature available where the chemical and biological control method uses at a specific time, at a single time. But here in this work, we try to use both the method at two different times. Basically, here we have the impulsive differential equation at two different pulses. So to develop the model, here we assume that the prey population or the pest population, because our main target is to control on pest population. So here we consider two pest population. The one is the targeted pest population and other is the neutral pest population. And this neutral pest population is available in the region of the consideration. And this basically population is the neutral and cannot attack on the crops population, but it is an alternative food for the natural enemies population. So basically, due to this neutral population, the growth of the natural enemies population will increase, and this increasement in the growth of the natural enemies will be useful in the control of the pest population. So that's why here we are considering two kinds of the pest. One is the targeted pest and other is the non-targeted pest, that is the neutral pest. And one natural enemies. So basically we have two prey, one predator model. And moreover, here we assume that the pest population is classified into two compartments, like susceptible and infectious compartment. So ultimately we have an eco-epidemic prey-predator model, and this is a very basic two-prey-one predator model where x1 and x2 are the prey population and y is the predator population. So you can see here x1 and x2 are growing in a logistic manner, and this y can predict both the x1 and x2. And here, since two preys are assuming at the same level, so that's the both the prey will compete for the food and other resources. So these are the basic assumptions in our model, where it is assumed that the susceptible population becomes infected in a saturation form, or we can say in form type 2 manner, because initially the infection will be very high, but after certain time this infection will be saturated. So that's why we are considering here saturated incidence rate. And the predator population will attack on both of the prey population, and the conversion can be considered in the holding type 2 manner here. And when the chemical control method is used, so a fixed amount like E1 into A3 will be harvested at every pulse, like T is equal to n plus k minus 1t. And due to the biological control, or due to the biological release of the species, the fraction P of the infected pest and fraction Q of the natural enemies, basically these are the fractions of the infected pest and the natural enemies which will release to control the pest population. So this is our mathematical model. And here X1 is the susceptible, X1 is the infectious, X2 is the neutral pest, and Y is the predator population. So you can see here, this is the incidence rate. So susceptible population becomes infected in the saturated form, and here alpha basically is the competition between the species. Alpha and beta are the competition rate, and R1 basically R1 and R2 are the predation rate. So due to these predation, there is a growth in the predator population, and this is considered here in the holotype manner. And now you can see here the last four equations are the difference equations. So here A1, A2, A3 basically represent the impact of the chemical on the pest population, and at another place the biological method is used. So here we release P quantity of the infected pest population and Q quantity of the predator population. Right? So this is the mathematical model, and in this model, the analytical finding, we obtain the positivity of the solution, boundedness of the solution, and with the help of some pre-established tools of the impulsive differential equation, we can easily prove that there exists a free periodic solution, and this solution will exist, and it is also globally asymptotically stable under certain condition. So here you can see these are some initial, okay, so here you can see these are the sufficient conditions like B20 minus something. So from this condition we can also obtain some thresholds for the P, Q as well as the T, and T here is the impulse period. So the theorem suggests that if T is greater than its threshold value, means if the P quantity is higher than the threshold limit, so the pest population will be extinct. Or we can say the pest extinction's periodic solution is globally asymptotically stable. Means for the longer time, this periodic solution remains stable. Right? So this is the condition where the pest population may be extinct, because our target is either to extinct the pest population or to maintain it at a low level. So under these conditions, here it is clear that if P is very high, then the pest population will be extinct, or if Q is very high, then the pest population will be extinct, and the similar conclusion can also be drawn for P1, P2, P3. Means if the chemical pesticides are used in a large amount, so the pest population will be extinct. And from these equations, we can also determine the value of T, means the thresholds for the impulse time period T. So this T suggests that if it is very less or the impulse period is very short, that means in a short time, if we are releasing or if we are using the chemical or biological method, then the pest population will be eradicated, right? So okay, if we are releasing the large amount, so this is the common answer, but here the mathematics will provide the exact amount, or we can say the optimum amount. So in an optimum quantity, we can effectively control the pest population, and this solution will be given by this kind of the mathematical problem, right? So this kind of the studies is very helpful for the farmers as well as for the scientists or the policymakers who can prepare the policy and effectively control the pest population, right? So here these are some thresholds for the P means infectious pest, and Q1 and Q2. Q1 and Q2 is nothing. This is the maximum. Q is the maximum of Q1, Q2, right? So this is the thresholds for Q. And similarly, we can also obtain the threshold for T. And now, these are two sufficient conditions for the permanence. Permanence, that means the lower bound is not zero. Means the population will survive between two bounds. Or we can say the population or the pest population will survive at a low level, because in the naturally sometimes it is not feasible to extinct any of the species, right? So we will maintain the pest population at a low level. So here these are the sufficient conditions which guarantee to to maintain the pest population at a low level. And these are the same conditions here, but P is less than the threshold and Q is less than also thresholds. Means here we have two thresholds which is dependent on the chemical control P1, P2, P3 and impulse period T. Right? So if this P is less than its threshold value, or if we need less amount, that means the pest population will survive, will exist at a low level. And similarly for Q, and if T is very high, impulse period is very high, then also the pest population will survive. And here, this theory is validated by taking some realistic values for the parameters, and which is estimated here. So here, this assumptions. Now, this is not assumptions. The fact is taken from one source, that is the kisankarela.net, and given in D2, since these are the growth rate of the pest population. So if each female stem bearer has a 1 to 3 masses, like per 10 to 10 days, and each mass contain 50 to 200 eggs. So from this fact, we can estimate our birth rate given. And in the similar manner, we can also estimate other parameters. So basically here we are trying to find out the parameters values from the realistic example, right? So that this realistic, if these realistic parameters satisfy our findings, so it automatically validates our mathematical model, right? So here we have estimated the parametric values in per day, and we have also used its rescaled values. So by using the rescaled values here, it is clear that if T is less than T star, then X1S will be extinct, and here X1I is infected pest, and this is the natural enemies population will survive. Why survive? Because we are impulsively releasing. So at a particular moment of the time, the densities of this population will increase. Right? So if the impulse period is very low, then the pest population will be extinct. And this is the same case when P is greater than of P star and Q is greater than of Q star. And similarly, we can obtain here that if T is very high, that is T is greater than T star, so all the population will survive, but here X1X will survive at a low level, right? And similarly, for Q is less than of Q star, and the similar, and here if we increase the impulse period at a very high scale, that is like T is equal to 20. So here we have an unpredictable kind of behavior. Means we are not sure whether the pest will survive or it will extinct, right? So here we have to maintain our impulse period is either less than T star or greater than T star, but if it is very high, so we have an unpredictable situation. Now, and this model is extended by incorporating another assumption, and the assumption is if we replace the growth of the pest population by some periodic function, because due to the actually seasonal effect, the growth of the pest population sometimes may increase or may decrease, because there are lots of examples in the literature where you can see that the particular the growth of the particular pest will increase in a particular season, right? So due to this kind of the seasonal effect, we have to consider the growth parameter in a function of time-dependent manner, or we have to replace by some kind of the periodic function, right? So, and the another additional assumptions is that in the last model, predator was considered in a single form, but here we consider the predator or natural enemies. Predator is natural enemies. So here we consider the predator in two forms, immature and mature, because the immature predator is not able to attack on the pest population. So only the mature predator can attack on the pest population, and this assumption basically will provide more realistic situation. So here we are considering the predator population in two life stages, immature and the mature population, and the growth of the pest population is replaced by some kind of the periodic function due to the seasonal changes or due to the seasonal variation. So here the birth rate is considered as a function of time, that is a function of the sine omega t, where where basically this epsilon signifies the extent of the seasonality, that is lambda is equal to v1 epsilon, indicates the magnitude of the perturbation in the and omega denotes its angular velocity. Right? So Ni and Nm are the densities of the natural enemies population immature and mature stages. And okay, so this is our mathematical model. So what is the basic differences between this model and the previous model? So you can see here we have considered two equations for the predator, and as well as here actually this PSNM. PSNM means predation of the susceptible pest population by the natural enemies. So this is considered here in the Hohenstein tool form. Right? So these are some basic differences between the previous model and this model. And v1 here is the function of t, not a constant parameter. So for this particular kind of the mathematical model, we can apply the same theory, right? And with the help of the same theory, we can suggest that there is a pre-free periodic solution exists for the system. So if suppose there is no pest population, then we have this 13 number equation, and this 13 number of the, for this particular 13 number of the equation, we can integrate between the pulses, and using the theory of the impulsive differential equation, we can determine its fixed point, and at the fixed point we can obtain the periodic solution. So of course the periodic solution is exist here, and this is the periodic solution for this system. So these are some sufficient condition. So you can see here in the sufficient condition, the cos omega t function is included here, and this function shows that the sufficient conditions is fluctuating periodically, and in the sufficient condition of the previous model, basically we have some fixed kind of the sufficient condition, but now we have periodic time sufficient condition. So we can also determine here the thresholds for the chemical control and for the biological control. And of course, we can also obtain the theory for the global stability and also for the permanence as the previous model. And these are numerical simulations here to validate our mathematical findings. And here we are considering the same example, right? So for the same example, here we can see that when p is greater than p star, so the prey population will be extinct, and when okay, so in all these simulations, the lambda is equal to 0. Basically, lambda is used here for the seasonality variation. So if there is no seasonality variation, then we have almost similar to the previous model, but the major difference is here we are considering two stages for the natural enemies population. So the findings is almost similar to the previous one, but if we consider, okay, so these are actually some sufficient conditions for the, these are the some threshold values. But if okay, so in this figure you can see here basically omega is the angular velocity, and considering like 2 pi, because the sine function is the periodic and its period is 2 pi, and that's why we are taking the value of omega is 2 pi. So if p is less than p star and omega is equal to 2 pi, then the system will be permanent, or we can say the pest population can survive along with the natural enemies population. can also obtain the threshold values for the impulsive period t when lambda is equal to 0, and same here for different parameters, for different threshold limits, like p1 is less than p1 star. Okay, so here we work on a rigorous mathematical analysis and try to obtain the thresholds for all the controlling parameters, and also try to validate all the thresholds with the help of some numerical simulation. And if we increase the seasonality variation like lambda is equal to 1.5, so you can say here we have an unpredictable kind of the behavior, right? So this is the figure when lambda is equal to 1.5, right? So in this talk, basically we will try to cover two integrated pest management mathematical model for two prey, one predator, and here we try to apply the chemical control and the biological control for effectively control of the pest population. And here we observe that if we increase the chemical control method, or if we increase the biological control method, then the pest population will be extinct. But we have to maintain, or we can combinedly use both the chemical and biological control method in a manner so that either the pest will be extinct or it may survive at a low level, right? So these are the main findings of this work. Now these are some important references which I have used. Yeah. So if you have any kind of the query or any question, so you can ask. Yeah, any question? Thank you. Thank you. Yes, any question or any doubt from the participants? I'm waiting. I think there is no question. So once again, I would like to thank to the organizer of this program to provide me the opportunity to share my knowledge, to share my views. Yeah, so thank you very much. So, Dr. Krishnan, what is the next guideline for me? So, can I read this meeting? Yeah, can I lead this meeting? Okay, thank you. Thank you for writing the comments.
Welcome to Dr. Vijay Kumar Jha.
Good afternoon, Dr. Krishna. Okay. Okay. Thank you. So, is my screen visible to all of you? Okay. I hope the full screen mode is visible to all of you. Okay. Okay. So, it is 2:52 right now. Maybe others will join very soon. So, first of all, I would like to thank the organizer, Dr. Krishna, for giving me this opportunity to share my work with all the participants and the distinguished guests. Thank you, Dr. Krishna. Earlier, in the last month, I have talked about some basic fundamental mathematical theory of neuroscience, calcium signaling. So today, in this short period of time, 30 minutes, I will tell about some glimpses about the numerical method that are used in the study of neuronal signaling. So today's topic is finite volume model to study calcium distribution in nerve cells. You can see on the screen, neurons are there, impulses are moving from soma to axon or dendrite to axon, that you can say. In the last lecture, we have talked about how the signaling occurs, which are the parameters are important for the calcium signaling. The second figure that you are seeing, it is a geometrical aspect of neuron. So that it is developed in our lab. But here we have used other methods to simulate this result. This is all about my profile. Basically, we are working on mathematical neuroscience. This is part of mathematical biology, in which we use usually as a mathematical concept, ordinary differential equation, partial differential equation. Earlier we have used, then around 2015-16, we have started on working on fractional differential equations models in neuroscience. Earlier we have used finite element method, finite volume method, and we have started on the fuzzy differential equation as well. nowadays. So you can see the neurons are there, but before that we will talk about some little bit about the finite volume method. What is finite volume method? That is very important here. The finite volume method that you can see earlier, we know about the finite difference method. Then we have studied about the finite element method, and then we gone for the finite volume method. So systematically, you can see the update in the numerical method. We can see what happens in the finite difference and element that we will compare in the upcoming slide. But here, I will talk about first the procedure of the finite volume method. Finite volume method, once we talk about, so it is basically the grid generation process that we can say. So the first step in the finite volume method is the grid generation by dividing the domain in pieces. In pieces, that is known as the cell as well. And we say it is a discrete control volume. Some echo is there. So what we see, as you can see on the screen, there is a straight line that we have divided into the 20 number of pieces. So nodes are there, it is stated as 1, 2, 3, 4 up to 20. So it looks like that we are talking about the finite difference method. But no, it is not finite difference method. We are talking about finite volume method. So what happens if you're talking about the one dimension? Suppose you have any pipe flow we are talking about. So the cross-section area, if you multiply by the length, then it will be volume. So in the three-dimensional process, we can also consider the control volume or finite volume in place of, as we can discuss that in the one-dimensional case, we can also discuss. If the cross-section areas are not regular, so piecewise you can define, and piecewise also you can define in the finite volume process. So that is the beauty of finite volume method, which is not available in the previous methods. We can say the finite difference method or element method. So the boundary control volume are also, it is midway between the adjacent nodes. Thus, each node is surrounded by the control volume or cell we can say. So according to control volume or discretized place, we calculate the values on the basis of left and right values. As you can see in the second figure, the supposed mid value that we are talking about, the point P. So one left that we say the west, and the right we talk about the east. So the value of that at the point P, that's depend on the value of west and east values. So ultimately it cover whole the area that we say the whole the volume in the physical way. A general node point defined by its neighboring in a one-dimensional geometry that we are talking about. The nodes of the west and east are defined by the W and E respectively. So the west face of the control volume that we refer as a W. Suppose you are talking about the heat mass flow. So if you're talking about the temperature distribution T, so that we defined as a TW and TE. And the point P where you are finding the value, that is TP. So the value of TP that defined for the on the basis of W and E. And accordingly, we will calculate on the boundary. On the boundary that we know there is no any west point on the first boundary. So there is a U alpha is there, and the last boundary U beta is there. So that will be calculated accordingly. That we define in such a way. Now we can talk about how we discretize. So it is a very most important feature of the finite volume, which depend on the integration of the governing equations over a control volume. So what we see, we discretize the equation also to yield a discretized equation at its each and every nodal point P. So according to point P, we define a system of algebraic equations. See, the beauty of this finite volume method is you are discretizing but you are using the same equation. So you integrate the equation all about as it is, which is not happening in the finite element method, where we require the weak form in the finite element method. In fact, in finite difference, if your geometry is irregular, there's no any possibility to use finite difference method. But if your geometry is irregular, you can apply finite element and as well as finite volume method. But in finite volume, the weak form is not required. Directly you can integrate over the volume. So that is the advantage over the finite element method. In one dimensional, I have told you that east and west part that you can calculate here. So center point that we define as a P, and left is the west and right is the east. So accordingly you can define. So the difference you can take equal, unequal, depend on the problem that you can define, because if your domain is irregular, geometry is irregular, then it will work accordingly. Suppose we are going for the two-dimensional case. So what will happen in along with the west and east part, you can calculate north and south part also. Suppose you are talking about this 8 number node that you were talking about. So you can calculate on the basis of 7, 11, 9, and 5. Suppose it is 7 here. So according to this boundary condition, 10, 8, and 4, you can calculate. So this is the beauty of this finite volume method. It's covered whole the volume accordingly. And the point-wise solution that you can get. So point-wise, you are getting the nodal value on the basis of the surroundings. That is the beauty of this finite volume method. Same way you can define for the three-dimensional case, upper and lower, that you can add in place of northeast and southwest, you can add upper and lower. After discretizing over each volume method, we are finding a system of algebraic equation that I have told you earlier. So you know the system of algebraic equation can be solved by any numerical scheme like Gauss-Seidel method. Suppose we are talking about what is difference in finite difference method and finite volume method. So thus I have recapped here. So in the finite difference method, what happens? It is the most direct approach to convert the governing equation to algebraic form. For each and every node, we discretize the whole area according to node. So a node in a space is considered for solving the discrete equation and is solved at every node. So at every node, you are also finding in the finite volume. But the thing is, here only node that you are calculating, but there you can calculate according to control volume. It uses the information only for the grid points of the approximation of any function that we are talking about. Finite difference is used mainly for structure grid, proper block like shaped domain. Suppose if you can see the cursor. So here, if these 4 domain, if I just delete from here, what we can understand, our finite difference method may fail to give the answer, or you can generate the dummy domain there. So ultimately, if you have the shape is proper way, then you can apply the finite difference method. So that's why finite element comes over this finite difference method. Regular grid can be used in some domains such as meteorological, seismological, and astrophysical simulations, where the process is throughout the same that you can do this. But what happens, suppose I draw one line between these two, any other line, we have to rearrange all the line accordingly, because it depends on the pieces how you are defining. So H and K that you have to define as a equals. H should be the difference. Suppose we are talking about in the x-axis, so H should be the same, K should be the same for whole the domain. So if you are drawing any straight line, you are not able to define in such a way finite difference. So it is very difficult to implement finite difference in curved boundaries. Curved boundaries means what? You're talking about, suppose here is some curve you are drawing, it fails to give the solution. I am not criticizing finite difference method because it is very useful for time domain, where finite element and finite volume do not works. So finite difference method is applicable for the time as well, whether you are using the finite element or finite volume. So finite volume method, what is happened? It is different from the finite difference because we are talking about a node. In this method, the entire domain is divided into small but finite volume called cells. So in the place of discrete point, we talk about the finite volume, that is cells we are talking about. So it covers whole domain. It uses the average from the cell finite volumes for approximation of any function. So I have told you the west, east, and north, south, upper, lower, everything that you can calculate accordingly. The third point is it is based on convergence principle. Definitely our solution will converge accordingly. The idea is that anything coming into the cell from one boundary need to leave the cell from the other boundary. So flux evaluation is possible in such a way. Any irregularity, if you see inside the cell, then it feel difficulty for this case. The governing equations are solved at every cell volume, where centroid for each cell represent the cell and consider to behave the average quantity of flow variable. So as I told, the point P is that is the centroid, and suppose this is a two-dimensional figure. So in such case, what happens? The east, west, left, north, south, everything that we can calculate at the point P. So in such a way, it gives the solution by considering the whole volume, whole space that is considered. Even though irregular shape is there, you can calculate accordingly. So this is all about the finite volume method. Now come to the some application. Some application in biological. I have told earlier that application of finite volume in the biological system, especially in the nerve cells. So what happens in the nerve cells? Suppose in the left-hand side, you can see the blue line that represent our nervous system. I hope those who have attended the last lecture, they knows the brain and spinal cord that define as a central nervous system, and the rest part that define as a peripheral nervous system. In this system, there are number of cells, nerve cells exist, and we study on the basis of nerve cells. So when you are going for a study of such nervous system, so again, keep in your mind which mathematics you are going to use. Either you are dealing with the ordinary and partial differential equation, or you are dealing with the system of differential equation. If you are going for the system of differential equation, then definitely the solution, bifurcation analysis, and the whole bifurcation analysis that is required. So model analysis, equilibrium point, everything that you require to study. But if you are going for the reaction diffusion equation, reaction advection diffusion equation, or we can say the cell model, that is required to study ordinary and partial differential equation way. So here the brain is spinal cord that we define as a central nervous system, and the rest of the part that we define as a peripheral nervous system. Now come to inside the nervous system. In the human brain, a number of different type of neurons exist. One neuron that I have considered here. As in the dendrite and the nucleus that you can see, and the later part, the axon, it is axon terminal is there. Some myelinated sheet, you can see it work as a catalyst. So what happens? The neurotransmitter, the nerve impulse that comes from the dendrite, it is executed in the neuron, and that throw out by the axon terminal. And there, in the axon terminal, there are a number of neurons are receiver there that they can receive the transmitters. So this is it looks like the simple process, but it is not like so. So what happens here? Now you can see inside the neuron, in the soma, the almost circular region that you can, circular in three-dimensional spherical region that you can consider according to the geometry, but geometry may be the irregular. So in that case, the finite volume is not, finite difference is not able to deal with such situation. In that case, the finite element and the finite volume that you require. I will show you one example for finite volume method. But how it works, that is important here. So a number of locations that you can see in mitochondria, endoplasmic reticulum, nucleus, many more things that you can see. Here, the Golgi apparatus is there. And the outside the synapse, it is also that is defined. So here you can see the axon terminal is there, and in the red bubbles form that you can see, it is a neurotransmitter is moving out, and the receivers are there for the other neurons that they are ready to receive neurotransmitters. Between these, it is known as the synapse or synaptic cleft. So this process happens due to some chemical contribution, chemical reactions. So what happens? The free calcium ion, this is our nature with the grace of God, only the free calcium ions are responsible for the movement of the neurotransmitter. So in such case, what happens? The free calcium ions comes from either from the synapse outside, or it may come from the internal source. So as the free calcium ion level goes to the threshold, it force to the neurotransmitter moves toward the synapse. So in such case, it goes to the synapse and the receivers are there, they can take part. In other conditions are also there, that is not in the figure that you can see. So gated channels are there where the synapse is not there. They are in touch with each other, and there is a gate, and via gate the neurotransmitter can move. So it is depend on the problem, which kind of situation you are handling, then you can define the mathematical problems accordingly. So this is all about how the neurotransmitter moves. So our purpose of study here, the fluctuation and the movement of the free calcium ion in the nerve cells. On the basis, neurotransmitter will move on the basis of if any kind of irregularities happening, then the neuronal disorder may happen. Neuronal disorder means what? Well-known diseases that you can see, that is the Alzheimer, Parkinson, any other disease, epilepsy is also there. So that occurs due to the irregular functioning of this neuron cell. So in such case, what happens? We are calculating the amount of free calcium concentration, and on the basis that we can do analysis. See, calcium is important. There's some other parameters are also there that may affect the free calcium level. Due to that effect, the movement of the impulse occurs. If these free calcium ions are, you can say, if it is higher, so more neurotransmitter will move from one cell to another cell. So it is very easy to understand. But biologically, it not happens. Biologically, if free calcium ion goes high and high, it becomes toxic. So if it becomes toxic, then definitely neuronal death process occurs. In some cases, partial damage also occurs. What happens due to irregular process of the free calcium ion concentration, movement of free calcium ion, some tangles and plaques may generate, cell will remain live, but some tangles and plaques will generate inside and outside the neuron cell. So due to this, what happens? Maybe the particular neurotransmitter may not move from one cell to another cell. Even though if they move, it is not in the particular way. So this is the initial symptom, sign of progression of the Alzheimer's disease. So that is very important to study such parameters which are important for the maintenance of the free calcium ion. So number of parameters that you can see, one or two I will tell you here. As free calcium ions enter into the cell via different manner, maybe the due to generation of action potential, or maybe the chemical signaling occurs. If the chemical signaling occurs, so physics is applicable, 15-second law, first law that you can apply. As it enters into the cell, a lot of proteins that exist near the plasma membrane. What happens? These proteins react with the free calcium ions and makes the calcium bond protein. This reaction process is what? Reversible also. So time to time it may increase the free calcium ion level and it can decrease the free calcium ion. So this process is known as buffering. So it is a buffering process, and that protein is known as the buffers. So such things happens also. So here we have considered in our model calcium buffering and some voltage gated channels that we can consider. Other than this, in the later part, we can discuss here. So as you can see, this is the structure of the cell. One part where we can talk about the voltage gated channels are there, synaptic cleft is there, neurotransmitter receptors are there, and numbers of ions is moving here. But only in this model we have considered the voltage gated channel and the movement of the free calcium ion via chemical signaling. So chemical signaling, you can consider the diffusion process, you can consider the advection diffusion processes. So what happens? The free calcium ion is moving inside the cell. There are buffers in the red color that you can see, and it reacts with the free calcium ion. It makes the calcium bond buffer. So calcium bond buffer, that is the chemical process is there. So some differential equation we can generate according to chemical reaction. So enzyme kinetics is required to study. So that you can see the A plus B is equals to C if you have with the rate of K1 and K2 in association and dissociation rate that we can define. So according to the law of mass action, the rate of chemical reaction is directly proportional to the product of activity or concentration of the reactants. I will not take too much time for this. I hope those who have attended earlier, they are familiar with these reaction terms. So dA by dt is minus Ka1 AB and plus K2 AC. So A is productive due to reverse process of the C makes again A and B, and it decreases due to the combination of A and B with the K plus affinity rate or association rate. So that's why we have taken the minus here, and here we have taken the plus sign. Same way you can define for dB by dt, you can define by dC AB by dt. So I'm just leaving these slides that are very, this is the physical process that you can consider for any biological, maybe the engineering students as well. I come to the model according to, have only 5 to 10 minutes I have. So this we have earlier discussed also. The same process you can define for the engineering point of views. So neuroscience, mathematics, and computer that require the ordinary differential equation, partial differential equation, and the fractional differential equation that we are talking about. We have applied finite volume, finite element, integral transform also we have used, and with the help of MATLAB console, multiphysics, we have used the simulation part. So in this piece of work, we can talk about the finite volume model to study the effect of VGCC on calcium distribution in nerve cells in presence of excess buffer. Excess buffer means what? We are talking about the buffering process. So this figure that is familiar with this. So chemical reaction that happens, CAB is equals to CAB, and its representative parts, respective partial differential equation that defined here in equation 2 with the use of Fickel diffusion law, law of mass action that also applicable. R is the reaction term, and here the first equation that we are considering here. So quasi steady state condition that you can talk about. So there is immobile buffer. There is no any movement in the buffer. We are fixing the buffer, and the respective CB we are fixing. The quasi steady state condition that you can define. So the voltage gated calcium channel that is formulated in equation 6, and the flux related to this is the current equation. So flux is what? I minus ICA upon ZCA F V astrocytes. Here we have talked about the supporting cell of the neuron cell, that is the astrocyte. In this paper, we have considered the supporting cell of neurons, that is astrocyte, and the process that is remains same. It also takes parts in the signaling process. So the steady state equation that we define here, since we are using finite volume method, it is related to the domain. So here we are considering the steady state, but you can go for the unsteady state by applying some Laplace transform or any method that you can apply along with the finite volume method. Finite difference also you can apply. So these are the conditions for our equation. So what happens here? The entire domain in the one-dimensional case, suppose we are talking about, we have generated the node, 20 nodes are there. We have talked about. I think 20, no, it is a mistake. 30 nodes are there here. So total, the internal node are 2 to 29 that we can consider, and the first and 30th node is considered as a boundary condition, where we can apply the boundary condition. So the between the nodes, the value, the total domain is length is del x, and half part is the del x by 2 that we have considered. So this is our desired equation. This is the second order differential equation that you can see, del square u per del x square. It should be d square u by dx square as time is not considered. So what we do, as I told you in the control volume, directly integration is applicable first. So if you apply the direct integration over the volume, del v is the volume that we are talking, we are applying this. So what happens? The second order is converted into the first order, and respectively that we define here. Now A is what? A is the cross-section area of the length that we are talking about. So A is over the cross-section area. For every term that you can see, the A is cancelled here, and your respective, the volume is what? dcx E minus dcx W. So east and west that we have converted here. And Cp is the value of calcium concentration at the point of P. So according to E point, what it is? Ce minus Cp upon del x. You understand the forward difference operator here, and Cp minus Cw upon del x here. Same way, minus A Cp del x plus B del x is equals to 0 we have considered here. Now, if you consider all Cp together, so what we get, it is 1 upon delta x plus 1 upon delta x plus A delta x Cp. That equals to 1 upon delta x Cw plus 1 upon delta x Ce plus B delta x. So this we are talking about the point 2 to 29, right? 2 to 29 that we are talking about. If you are taking the 30 nodes, so 2 to 29. If you are talking about the 20 nodes, it will be 2 to 19. So this you can consider as a system of equations where unknown are Cp, Cw, Ce are the unknowns here. Ap, Aw, Ae that is calculated according to the delta x. Su is what? B delta x that you can define. So in this case, Ap, Cp is equals to Aw, Cw plus Ae, Ce minus Su that you can define. Now we can go for the node 1 and the last. Whether it is 20 or 30, that you can consider the last node. For the first node that we know, the Aw will be 0 because there is no any point is in the Aw. And Ap will be what? Aw plus Ae minus Sp. And A is 1 upon delta x that we know. So in the case of Sp, here we have considered 2 upon delta x plus A delta x. And Su is what? Su is what? It is defined for the boundary condition. Ca that we have considered the first boundary condition. Same way we have considered here for the second boundary condition. So as after implementing all the things that we have talked about, all the nodes we have finished. Now the whole system is converted in the form of Ax is equals to B. Either you can understand the system of algebraic equation, or you can understand as a matrix form Ax is equals to B. Then we apply the well-known numerical method, Gauss elimination, Gauss seidel method that you can apply, and you can solve the problem. To simulate the result, we have used these parameters here and some graphs that we can see. Here we have considered the B beta, that is the buffer consideration, that is 1 to 30 micromole we have considered, and the result that you can see in the diffusion way that you can see. For different buffer, different impact is there. Since B is equal to 30 is a maximum, so it is lower down the free calcium concentration level as it reacts with the more free calcium ions. And the blue line, you can say in absence of the buffer, it will be higher. So there is a chance the nerve cell may be the toxic. In this case, we have considered the astrocyte. So astrocyte also become calcium is also toxic for the astrocyte, so there is a chance for this one. In that case, the impulse will move accordingly. Here, the affinity that we have applied, suppose buffer concentration has a different affinity because number of buffers exist there. So according to buffer, we have calculated. So as you can see, as you increase the affinity, it will decrease rapidly compared to the less affinity buffers here. Here we have talked about the affinity where the voltage gated channel where the voltage difference is -65 and -85. So cell wise you can see here. So it will generate accordingly at the -65 and it will generate accordingly the what? So according to this you can also study. Here, the flux condition, the diffusion coefficient we have measured. If we have the more diffusion process there, so definitely more free calcium ion will come join. So the peak value will start at the maximum, then it goes to the lower. So many more things can be discussed if time permit, right? So it is up to the finite volume method that we have used in the biological process. Many technical things that we have not discussed right now. It can be discussed later. So these are the few references that you can see here. So basically, we are working on ordinary, partial, and fractional fuzzy differential equations, and we have applied finite element, finite volume, some analytic solutions also. We have obtained for the 2 and 3 dimensional problems. MATLAB consoles are also used to generate the result earlier. These are some books that we are talking about. So these are few publications that we are talking about here related to mathematical neuroscience. So I end with this. This is the team member of our lab, we can say. So thank you for all of you for listening carefully. If you have any question, you can ask me. And again, thanks to Dr. Krishna for inviting me, giving me chance to share my research work. Thank you. If you want the slide, Dr. Krishna will definitely provide you, or you can also ask me, I can give you the slide accordingly. Thank you. Okay.
Our next speaker is Dr. Haratma Maiti. So our next session will start from 3:40 p.m.
I am audible, madam? Okay. Thank you, madam, for inviting me and giving me the opportunity to present my work in the great platform. Thank you again. Madam, my PPT is visible? Yes, just a minute. Yeah, now clearly visible? Okay, okay. So, good afternoon, everybody. Actually, I am going to present some problem on a real world problem. Basically, my title of my talk is Modeling of Reynolds Stress Equation and Predicting Their Terms. So actually, almost all fluid flow are turbulent. Actually, in real system, the laminar flow is very few. So see, actually, I am also from mathematics background, but I am going to show some physical problem. Basically, the problem on a river. So we considered the river problem, and we we formulate this type of problem using mathematical model. So this is our river system. See, this is the typical river picture. And see, when the flow comes from one end to another end from the river, so this type of phenomena occur due to the turbulence. Actually, see, this is some pebble in a river bed. There are two pebble is there. Due to the flow is obstruct due to the pebble and flow been separated. Here, same thing, the breeze. Everybody will learn that the breeze is here due to the breeze pillar. The flow been separated, and the flow been separated and occurring the like a vortex flow, eddy motion. So due to the obstruction flow, different type of flow and occur eddy motion. So due to the actually flow reason, see, due to the flow, this eddy motion, this is a bank failure, river bank failure. This is the practical application for the river flow, and the bridge have been broken. So this type of problem we are going to simulate. This for all left hand side, two pictures from the real picture, and this is the simulated one. This eddy motion we are going to simulate using the mathematical model. This is our typical vector plot using the data. We plotted the data in this. There is a circulation region is there, and see. So now actually, or what I already explained, the fluid when the fluid flow can be classified two categories. One is laminar flow, other is turbulent flow. Laminar flow is such fluid flow. Fluid moves smoothly or regular path. Actually, this type of flow may be considered as a well transport through a thin tube, and almost all flow are turbulent. Actually, the nature of turbulence multiscale, nonlinear, three-dimensional, unsteady, viscous phenomena that occur in high Reynolds number. Turbulent flow is irregular and random. So this is basically the study of turbulence, indispensable in engineering to investigate the structure of turbulence in very maximum in engineering structure to develop the engineering structure. So see, actually I am going to how to classify physically turbulent laminar. See picture A. This is the typical laminar one, and B, the periodic wavy laminar, and C picture, this C is type of a turbulent flow. And C, the how to laminar to turbulent, this is basically Leonardo da Vinci sketch. 500 years ago, Leonardo da Vinci sketched this type of picture, how laminar goes to turbulent, and there is also transitional zone also. See this region to this region is the fully laminar flow, and this region is transitional, and then chaotic motion, the turbulent. So actually we know that the Navier-Stokes actually to study the fluid motion using the mathematically the Navier-Stokes equation. We all well known the equation for Navier-Stokes equation. If you consider the Navier-Stokes equation for laminar flow, this is very much difficult to solve completely. Basically, theoretically, exact solution is very much difficult to get the exact solution for Navier-Stokes equation. So for even if consider the laminar one, if you consider the turbulent one, is very much complicated and cannot be solved. So then how to solve the Navier-Stokes equation, Navier-Stokes equation for turbulent flow. So now actually this is one minute. Hey Asha, আমি লেকচার দিচ্ছি ওকে রাখো ওদিকে। Methods of averaging and Reynolds decomposition. Actually, this is basically time average. So u bar equal to 1 by t integration t to t plus t u dt. T is arbitrary time. Capital T is time over which means is taken. T should be sufficiently large for আশা তোমাকে আমি লেকচারটা দিচ্ছি না Sorry to interrupt. Hello, I am audible? Yes. One minute. My PPT is visible, madam? Again? Yes. So, what I said, actually for laminar, if I consider laminar flow, the Navier-Stokes equation is very much all. So, to get the exact solution for Navier-Stokes equation for laminar flow, it's very difficult. But if I consider the turbulent one, is also more complicated. So what we will do? So for this, so we define the Reynolds averaging basically mean u bar equal to 1 by t integration t plus t u dt. Small t is arbitrary time, capital is the time of which the mean is taken. T should be sufficiently large for reliable mean value. This is called a time averaging. So the actually for turbulent flow actually u equal to u bar plus u prime, v equal to v bar plus v prime, w equal to w bar plus w prime, p equal to p bar plus p prime. So if we take the average for fluctuate, basically u prime is the fluctuating part, u bar হচ্ছে mean part, or u is instantaneous. Similar v, w and p. So if you take the average of fluctuating part, averaging fluctuating part should be 0. For u is the x direction velocity, v is the y direction velocity, w is the z direction velocity, and p is the pressure. So u prime bar and v prime bar and w prime bar equal to 0, and p prime also 0. And this is basically the operating rule, averaging rule. This is called the Reynolds decomposition rule. So for this, the decomposition we will use for Navier-Stokes equation. So this is basically the Navier-Stokes equation for laminar flow. So laminar flow for laminar flow, the Navier-Stokes equation is this A5, A6, A7, the equation of motion, and A8 equation of continuity. So equation of motion and equation of continuity constitute a Navier-Stokes equation. So what we already discussed, u equal to u bar plus u prime, v equal to v bar plus v prime, w equal to w bar plus w prime. This is basically time series data. So basically, if you take record the data for any instruments like a acoustic Doppler velocimeter or current profiler, so we will get that this type of time series data. This, if you consider the stream-wise velocity, that means x direction velocity, this is a blue line. So this is this fluctuating part, this is mean part, and this is fluctuating part, this is mean part, and this is the instantaneous part. So u equal to u bar plus u prime. Similarly, v equal to v bar plus v prime, w equal to w bar plus w prime. And using the Reynolds decomposition, so we use the Reynolds decomposition in the Navier-Stokes equation. So this equation. So then we calculate all the term, and then we get the Reynolds average Navier-Stokes equation. I come to this equation only, equation 5, 6, 7, 8. Please see this equation. Total number of equation is 4. 1, 2, 3, 4. How many variables there? 10 variable. U bar, V bar, W bar, P bar. 4 and 6 component of Reynolds stress. U prime, V prime, U prime, W prime, V prime, U prime, U prime, W prime. U prime, V prime, U prime, W prime, and V prime, W prime. U prime square, V prime square, W prime square. Total 6 component. 6 plus 4, 10. Total number of variables is 10. Six plus 4, total number of variables 10, and equation number 4. So this is not a closed system and cannot be solved. So then what we will do? So if we arrange the trace matrix like this, 6 component of Reynolds trace. So the Reynolds trace equation is not possible to solve completely theoretically. So we will model the Reynolds trace equation another way. See, and what we already explained, the equation, the Reynolds trace equation 5 to 8, there are 10 unknowns, namely 3 component of mean velocity, pressure, and 6 component of Reynolds trace, and hence the system is not closed. While the system of Reynolds trace equation is not closed, cannot be solved, so it requires some other relation among the Reynolds trace and the mean flow quantity in order to solve the equation. Therefore, in order to make clear turbulent structure in open channel flows, we investigate the Reynolds trace individually. So see, the most actually for turbulent flow, if we see the Reynolds trace equation and the Navest equation, see. So I go back the previous equation, the Reynolds Navest equation for laminar flow. See the laminar Navest equation for laminar flow. This equation and Navest equation, the similar one, only changes the mean part. See, and extra term is that 6 component Reynolds trace. U prime square, V prime square, W prime square, 3 1 3 1 2 3, and U prime, V prime, U prime, W prime, and V prime, W prime. So only change that. So now I am going to model those most important part for the turbulent one. So we will model individually. So first of all, we consider the XZ plane. So for XZ plane, what are the velocities there? X component velocity and Z component velocity. X component velocity means U and Z component velocity is W. So see, so basically this is basically all the U prime, W prime. So suppose if we will model based on the data. So suppose, so at any instant t, the suppose some instrument giving the data for each second 40 data. So if we take the 3 minutes data, how much data? 7,200 data. So for this data, we will eliminate or event, we will call an event. Suppose first of all we consider the XZ plane. For XZ plane, X direction velocity and Z direction velocity. X direction velocity is U and Z direction velocity is W. For turbulent flow, fluctuating part is most important. So we'll consider the fluctuating part. So for U prime and W prime, we eliminate 4 different quadrant. U prime get at 0. If U prime get at 0 and W prime get at 0, the event name is called the outward interaction. The event name U prime less 0, W prime get at 0, the name is ejection, and U prime less 0 and W prime less 0, the event call is inward, and the event U prime get at 0 and W prime less 0, the event name is sweeping. So now the total, suppose initially suppose we have a data 7,200. We eliminate 4 quadrant. Total number of, suppose this is quadrant 1, 2, 3, 4. So total number of event we distributed 4 quadrant, and suppose the total number this, suppose we have a data 100, suppose initially suppose number of data is 100. So suppose here some percentage of there, some percentage of there, some percentage there, and total number of there 100. So now, so suppose schematically I am going to show the sub sketch. So suppose the Reynolds shear stress can be defined as tau equal to C here. Reynolds shear stress can be defined as, suppose XZ plane. XZ plane can be defined as tau equal to minus u rho u prime w prime bar. So we divide the total number of 4 quadrant. So first of all, suppose if I consider the first quadrant, u prime greater 0, w prime greater 0, then the quadrant event, this is positive, this is positive. If I multiply two positive quantity, then this should be also positive, and the Reynolds stress minus u prime w prime bar should be negative, and Reynolds stress, the second quadrant, should be greater than 0, and this is also negative, and this is equal to positive. So now we just explain mathematically. So suppose Q1 event, outward interaction I equal to 1, u prime greater 0, w prime greater 0. Quadrant 2 ejection I equal to 2, u prime less 0, w prime greater 0. Quadrant 3 inward interaction I equal to 3, u prime less 0, w prime less 0. Quadrant 4 sweep I equal to 4, u prime greater 0, and w prime less 0. Basically, sorry. The total number of Reynolds shear stress, basically the total number of Reynolds shear stress u prime w prime bar. So for each quadrant, suppose we have a 4 quadrant. For each quadrant, suppose quadrant I. So for quadrant I, the stress fraction, suppose the contribution of Reynolds stress for quadrant I, we define this one, equation 9a. And equation 9a, basically u prime w prime, I is a number of, I means quadrant numbered, and a is the threshold parameter. Basically, I define the strength of the turbulence. So this is basically the definition. Limit t tends to infinity 1 by t integration 0 to t u prime v prime into I indicator function. Indicator function takes the value 1 if ith quadrant and 0 otherwise. And then through the stress function can be defined as the contribution of events divided by total number of events. And it is importantly says that the S10 plus S20 plus S30 plus S40 equal to 1. And this is basically experimental representation. And then what we'll do or these SIAs, or using this statistical analysis and mathematical model, we will try to model SIAs in theoretically. How to do this? Actually, what I said, the turbulent flow is random, chaotic, multiscale, non-linear, and unsteady viscous phenomena. Random means the randomness. Then there the explain to explain the turbulent phenomena mathematically, so their description demands the statistical approach because the randomness is there. So what I will do, so here then we consider the xz plane. Xz plane, what are the variable u and w? Actually here for turbulent flow, the fluctuating part is most important. So u prime and w prime are variable. Variable means this is basically random variable. So this two random variable is there. So now we normalize the random variable u prime w prime dividing by the root mean square, basically intensity of u and basically random standard deviations is each of the component. We define the u hat equal to u prime by sigma u w and w hat equal to w prime by sigma w, and then we consider the probability joint distribution p u hat and w hat and its characteristic function called as psi alpha beta and the moment ust by mst and corresponding cumulant qst. The following definition is there. This is basically characteristic function definition, moment and cumulant. And then if you take the Fourier series, then we get the basically density function. See, and then expanding the psi alpha beta in Taylor series about alpha equal to 0, beta equal to 0, then we get this is basically the Taylor series expansion is 13, and then we basically our aim is to compare like power of this each term, and then we'll able to get the relation between cumulant and moment. See, this is basically our relation cumulant in terms of moment in terms of cumulant. Moments, the second order moment. See, this is the moment in terms of cumulant, and then cumulant in terms of moment. From the definition, the moment defined as mst equal to u hat bar w hat u hat s and w hat t, and basically m10, that means this one, and basically 0, and then here for our model m1 basically correlation coefficient we have taken the negative one, so called r, and then we substitute the values of each component, and then we get simplified form of the cumulant. This is our simplified form of cumulant, and then we substitute the earlier equation and then get this ln psi alpha beta, and then get this equation 21. And if I take the inverse power series, then we get the joint density. Actually, I'm going back our sketch. Actually, our aim is to get the mathematical form of this tau, Reynolds stress, basically shear stress. Tau means minus rho u prime w prime bar. So if we get the mathematical form of each of quadrant, and then we'll get the total of and we'll add all the mathematical form of this quadrant, then we'll so this is our aim, and then we get after all simplification, we get the mathematical form of u hat and w hat, and then this is basically the normal normal distribution, and h is the Hermite polynomial of order s plus t into variable, And this is basically Gram-Charlier estimation. And we'll take the marginal distribution of each component. Then we get the functional form of U, basically U hat, and then W hat, and then sub C. This is this equation 23, basically the joint distribution of U hat and W hat. If you take the change of variable, then we'll get the functional form of tau n. Here, basically, our aim is to get the functional form of the total shear stress U prime W prime, and then here we will take the change of variable marginal function of tau n. Then we get the probability density of tau n. So see, the P Q1, Q2, Q1 is the first quadrant, Q2 second, Q3 third, and Q4 fourth quadrant. See, total shear stress can be written as this one, and then we calculate each of quadrant, and then we add the functional form, and then get the functional form of the total shear stress. See, all the calculation is there, and then basically all the mathematical calculation here. So for time constant I am going to skip those things. Just I am going to the final form. This is or the final form of the total shear stress, and this is our final form of the stress fraction, what I already explained. And this is our mathematical form, and then we compare our theoretical model, the first of the available data, how it match. So I'm going to that part. See, this is our joint probability distribution function, and then see here the triangle, star, or the observation, and solid line and dotted line are our theoretical model. See, the theoretical model and the observation good match, and this is basically streamwise velocity, and this is vertical velocity, and this is the Reynolds stress tau n, and this is the stress fraction. So it shows that our theoretical model is very much accurate with the observation. So the result and discussion, the proposed model shows very good agreement with the experiment delta, mathematical model of turbulent flow parameter like velocities and Reynolds stresses, leading to the identification of the 10 of the coherent phenomena in turbulent boundary layer. Concluded that for understanding the turbulent phenomena up to cumulate of order 3, actually earlier calculation what I shown, the more complicated. So for the simplification of my mathematical calculation, so we consider only the cumulative of order 3. So here for the study for the phenomena to study the phenomena of turbulence, so the third order cumulant is enough in terms of Gram-Charlier probability distribution of two variables. The third order moments of velocity fluctuation is directly related to the coherent structure through the turbulent characteristics. Sequence of events in bursting process, that is ejection, sweep, both interaction, is directly related to the turbulent energy budget in the form of turbulent diffusion. See the reference, it is basically the great paper bursting phenomena C in Nature. So the motivation came from this Nature paper. So thank you. So any question, please? Hello, I am audible. So, thank you, madam, and thank you all for your patient. Thank you.
Thank you. Okay, thank you. I am sharing the screen, right? Is the slide visible? Okay, thank you. So, should I start? cannot find the whole screen. Yeah, I am trying to find the full screen mode, but I cannot find there. I am trying to again share again, right? Please wait. Is it okay now? Okay. Thank you so much for inviting me to present my work in this very prestigious faculty development program. So I am now going to present my research, usually based on optimal control. So the title is The Role of Optimal Control in Modeling the Immunotherapeutic Treatment of Non-Communicable Disease. Actually, I am working in several areas, but here I am discussing very little about the non-communicable disease. If you go to my website, you can find more about in many other diverse areas working in applying in this optimal control in the real life application. And presently I am working as the president of Bangladesh Society for Mathematical Biology. It is the founder president, established in Bangladesh in 2020. And also I was the vice president of Bangladesh Mathematical Society and many other several organizations as well, and in journal, associate editors in Gonit, the Journal of Bangladesh Mathematical Society, and also the Journal of Khulna University. So, as usual, usually I go for discussing about some basic notions of optimal control problem and how this optimal control problem arises in our real life application, especially in the modeling of biological system or biomedical system. And then I will discuss one or two applications what is directly related to optimal control, especially the use of optimal control or introducing the optimal control in non-communicable disease. So this is the very brief outline of my talk. I don't know, the time is short, so I could complete all the details about here. So, but from the very beginning, I would like to discuss about the very fundamental notions of dynamical system, because modeling actually is nothing about some derivatives of the dynamical systems or the time derivatives of the dynamical system. So how we can present this dynamical system of our real system in our real applications in mathematical way. So this is the very beginning of introducing dynamical system or differential or difference or delay, such type of, that is the equation of the time derivatives. So this is we call initial problem, what is related only the state variable, and actually the time here is t, and this represents any dynamics where the system has the evolution over the time. And here we can define f, actually the function. Of course, when this type of dynamical system should have the solution, this f, that is the function, should be continuous, And if the solution should be exist, unique and existence, of course, the function of the first derivatives should be continuous and bounded. And the set of the initial points, it should also be the compact. So all these together make the system dynamics, which evolves over the time. But what happened when the system have some external dominancy of our influence? That is, if we have any type of influence on the system, if we can monitor the system in our own way, this system can be modeled using or introducing some control variable. So this control we can define as U, and the control of course should be bounded in some measurable set U. And when you introduce this control in this dynamics, you can see our dynamics should like appears in. But here the slide is moving. I don't know what is the problem. Is moving? So what happened? Is the slide moving now? So it is okay to see the slide visible. If I go for the full screen, the slide, I don't know, it is not moving. I don't know. Can I present this way? You can see this? Okay, very good. So this type of control dynamics should like appears in this way. That is, in this case, the function is like x, and also another component, another argument is u. That is, this u is the control variable, and of course the initial point as well. So this system is called the control dynamics. Here important thing is, when this control can be partitioned in different stages in different way, we can define in this way, or we can define in any other ways. Our figure, our system behave like what we would like to define our control in the system. So in this way, the control looks like the control system, and x is the state variable, u is the control variable, and our figure, you can see this type of figure like this one. So here, when our initial point x naught, and then at the time t1, our control, that is the state trajectory, looks like this one here. And when t2, the state trajectory comes appear here. When time t1, so this partition give us a very controlled dynamics, the control behavior of the system in our real application, in any real biological system or any other system. So actually, when we go for the general form of this type of formulation, we can write our objective function here. So we should have an objective function. That is, this objective function, of course, looks like in this way. It is the minimize or maximize this objective function, and subject to some dynamical system, subject to some dynamical constraint. This constraint actually the differential or difference equation. And of course, there are many other initial conditions, initial constraint or terminal constraint. Of course, there are some other constraint like the physical constraint. That is, this constraint should be mixed constraint or a state constraint. All these together give us a very complete scenario of the dynamic optimization problem. That is, this dynamic optimization problem is actually the optimal control problem. So now we can summarize how actually optimal control problem works. So this is actually the one kind of branch of optimization. What is we call the dynamic optimization. Here, the main aim is to find a control strategy for a dynamical system over a period of time such that the objective function should be maximized or minimized subject to some constraint. We can give an example here. What is the dynamical system? Actually, the dynamical system, a spacecraft like this with the control here corresponding the rocket thrust. An objective must be to reach the moon with a minimum fuel expenditure. So any kind of system we can make our dynamical system, and we can define our control, and we can define as well as we can find our objective values, objective function. Nation's economy is another dynamical system. Objective is to minimize unemployment problem, and the control in this case should be fiscal or monetary policy. So this is actually real application we can see in our everyday life. We are defining this one. So dynamical optimization and the optimal control actually the same thing and the same problem we can define. We can say either optimal control or the dynamic optimization problem. So we can define here, this is our objective function here. This objective function actually J have two parts. This is another one parts comprising the initial and the terminal conditions, and the another part is this one. All these two parts together give us the objective function which should be maximized or minimized. All other things are the same way I defined in the previous slides, and you also the control variable I can define in the similar way. And this is the actually the general form of optimal control problem. Minimize this type of objective function subject to some constraint. Actually, this constraint should be involved with our dynamical equation, differential or difference equation or delay equation or stochastic equation, so on, and including our control function in our control variable or our control strategy, and also including some constraint. This constraint should be mixed, or constraint should be a state constraint with all other initial and terminal conditions. And all the functions, all the involved here are defined explicitly in the to satisfy the solution of this type of optimal control problem. And this part is actually objective function or payoff. And this first part, it is called the salvage cost, because usually in the economic problem, this is usually defined as the salvage cost. But in the another type of problem we call the terminal cost, or as this is the different way we can define. And the second part is, it is actually the integral cost. So these two parts can be together, we can define in different way to convert one kind of problem to another. So there are another issue for the three kind of optimal control problem. Actually, I am not going to define this one as here. But another important thing I can show here, if the time permit, another example, or a physical constraint have a very important role to satisfy or to find our objective function optimized. So this physical constraint should have, I already mentioned that it should be mixed constraint, a state constraint, or all others in terminal constraint. But this is have a very good role when finding the unique solution or unique values of our objective function. What is our main goal to solve this type of problem? And the solution of this type of problem is important because we need to verify whether the solution exists, or if the solution exists, is it unique, or so different thing should be verified using different types of theory. And of course, theory is important behind any numerical scenarios. So you can go for, if we want to go further for the numerical simulation or numerical results, before that we need to verify when the model is actually has the solution or the unique solution. So optimal solution should be, of course, should be found. So this optimal solution can give us the guarantee to go further for the numerical comparison, the numerical validation. And when we can get the optimal solution, this minimizing or objective function looks like at the objective values it should be either minimized or maximized depending on our problem. So this is actually the target sets, or this is actually the aim of the solution. You can see there is a lot of set of solutions here. All the solutions should have the feasible solution, but only the optimal solution is the red one. So, and when we get the optimal solution, our objective function looks like this one. So this is called actually the well post of the solution. Okay, so now how we can get the solution? It is actually very important to use the Hamiltonian to get the necessary condition for the solution. If you want to get a single solution, actually it is not possible to get a single solution from any optimal control problem, because the solution actually is a set of conditions, set of necessary conditions. So this set of necessary condition can be obtained by introducing the Hamiltonian like this way. This P is called the co-state variables, and also the lambda is a constant, and this lambda should be 1, because otherwise the solution would be degenerate. So this, in this way, this type of optimal control problem is the normal form when the lambda is 1. And when we differentiate with respect to u, that is the control variable, we can get optimal condition, optimality condition at the point u star. And the other condition are the transformability condition. The last one is, this is the corner condition, and this is also the adjoint equation. We can get the other part is the adjoint equation. So optimality condition and 2 equation is called the adjoint equation, and the third is the transformability condition. All these conditions are called the necessary conditions of to solve the optimal control problem. One important thing I can mention here, that about the bound of the control, because the before in the necessary condition I cannot define, I cannot impose any bound on the control. But if you don't put any bound on the control, in that case the solution can be unrealistic in many cases, in sometimes. So control should be bounded in a subset of R, and this type of boundedness actually impose the Pontryagin maximum or minimum principle, and in that case the solution looks like in this way. And of course this is called the necessary and sufficient condition, and this necessary sufficient condition is actually Pontryagin maximum or minimum principle. We usually use, many authors use Pontryagin maximum principle or minimum principle, but what is the main scenario in this Pontryagin maximum principle is here, and this is a very strong condition, because both necessary and sufficient condition are this Pontryagin maximum principle. So we should care about the bound on the control. It is very important. Just see the example here. If we don't put any bound on the control, this type of case solution may be unrealistic. You can see the solution is unrealistic when there is no control in bounded, in the first example. In the second example, there is a bound on the control u, and then the solution is actually immediately not going to the negative part of this in this graph, you can see. So this is actually the real scenario when we get the solution of the control problem. So now actually we need to introduce this type of control strategy in our real application, in our everyday life. So I am discussing here about one type of problem, one type of a non-communicable disease. So there are several types of non-communicable disease, like the cardiovascular disease, like the cancer, like the leukemia, blood cancer, and different other parts, the diabetes. You can apply in different parts. You can introduce in different type of disease. This is the chronic disease for in our everyday life, and there is a lot of life threats for this type of disease. But before that, actually, when we formulate this type of model using the control or without using the control, we need a basic formulation. We need a basic strategy how we need to formulate this type of model. You can see all we are here the fellows, students, researchers or scholars who are working in this area, they know how to formulate an epidemic model. There are very small, very in general, very simplified case is the basic epidemic SIR type model. So this is the multi-compartmental model. SIR type is the 3-compartmental model. This is the very fundamental compartment. But many students, actually, when we don't know how this minus is appearing here, this minus you can see, this susceptible is those people who can have the vulnerability to get infected. And this type of disease, when the susceptible people goes to close contact with the infected one. So this infection occurs at the rate of beta. And this is called the force of infection. And this type of disease only gives the minus sign. And this is actually the model we can formulate, we can model this susceptible case. And immediately this type of number goes to infected class, infected compartment. And the other part is usually the recovered, some with some immunity, and sometimes the disease induced death rate when there is a disease or infection. And when this part is the recovery part, this recovery part minus immediately gets into the compartment R. So this is the very simplified model with some initial conditions. But when this disease is endemic, you know, or most of us we know what is epidemic and endemic. Epidemic is actually very sudden outbreak, but endemic is not a sudden outbreak. It continues in a locality, it continues in a region or in a country for a longer period, or it appears frequently, periodically in a region or in a country. In that case, we need to consider the demography, that is the birth rate and death rate, both cases in this model. And thus immediately considering this, the model gives this type of scenario figure. So this is a very simple model. You can, if you understand, we can formulate the model with our own way and considering different types of disease and the nature of the transmission of the disease. Now, what happened when this type of disease we consider in the 4 compartment? If we consider the incubation period, it is important sometimes to consider incubation period, because most of us knows during the corona period, the corona only the disease, the viral disease, which have a very long incubation period. We know all of us we know, and in that case we must consider another compartment E, that is, this is called the exposed or latent, when the incubation period happened. But all other things is the similar way. So only this type of disease is the very general form of SIR model. But sometimes some disease have the reinfection, especially corona is also have some reinfection. So when recovered happened, this type of recovered people immediately goes again to susceptible. So this is we call the SEIRS. That is, we call the loss of immunity. When the immunity is not permanent, we can consider this such type of model is SEIRS. So considering actually the nature of the disease, we need to formulate this model which is appropriate, appropriately explain the real scenario of this type of model. So anyway, now I can go for a application in our non-communicable disease, because several non-communicable disease have a great threat in our real life, especially the cancer. Leukemia is very important, another fundamental and very life-threatening or life-killing disease, this cancer. And we have this cancer model, a many citation, when one of my students did such type of a model in her MSc or BSc thesis, BSc results. So we can see what is leukemia. We know that leukemia actually one kind of blood cancer, but what is blood is produced in our bone marrow, we know. when blood is produced in our bone marrow, but sometimes this blood have the three parts. All we know is the blood have three parts: blood, red blood cell, white blood cells, and the platelets. And platelets, all these things, and the white blood cells have the spleen and the lymph nodes. And usually all the blood cells have the usual dividation, the natural dividation. But when cancer appears, when the cancer occurs, when the tumor occurs, actually this natural division does not happen, and this division have an abnormality, and the abnormal division give us a very unrealistic growth of our blood cell, and this is actually called our cancer. So when the cancer is identified at the very last stage, it is very difficult to survive or to sustain such type of patient in our society. So early diagnosis is very important to cure or to prevent such type of cancer or such type of disease in the real life. So now, what happened in our body? We can consider three type of cell inside the body. It is a very simple model, and we can explain this situation inside the body in this three type of, using this three type of compartment: susceptible compartments, infected cell, and immune cell. So susceptible cells are those cells who have the vulnerability to get infected by cancer cell. And this, when it is already infected, this is the infected cell, this is the cancer infected cell. But there are some other fighter cell inside the body, we call it the immune cell. So immune cell, actually our main aim is to increase this immune cell, or to increase the immunity inside the body, when this immune cell can fight against the cancer or against any viral disease. Actually, this work was published in a very good journal. You can find this in this website. So when we consider these three components, we get SIR type dynamical model. Still, we don't apply any control measure in this model. This is the very transmission dynamics inside the body, cell to cell transmission inside the body. So this is the case A. This is the source trap, and all of these other parts is the disease. This is the part of the infected cell. It immediately goes minus, and it comes here in the negative. With infection is the part, and there is a disease induced death rate. As usual, I explained in the before slide, and here you can define such type of immune cell is like this is on, it comes here, immediately comes here, and this is the natural death rate, it goes from here. So this is the very fundamental and very simple model we can consider here. Now, if we go for the treatment of this type of cell, that is, this treatment actually in the nowadays, very important treatment is the immunotherapeutic treatment. Immunotherapeutic treatment, what is this? We should know that. What is immunotherapy? Immunotherapy is actually very most effective variety of chemotherapy, which can not only kill or halt the pathogen, but also increase the long-term internal resistance for our immune system, so that the body can itself fight against the virus. And this type of therapy, actually, you know, anti-cancer immunotherapy, what is we know the CAR T cell therapy, and it is also another language we call it engineered T cell therapy. So engineered T cell therapy actually is a very promising treatment strategy now in the cancer treatment. So now I can define what is the engineered T cell therapy. Engineered T cell therapy, actually, it is now the lab developed immunocell, lab developed cell. When we can transplant a cell from a healthy cell from the body, it put in the lab, and then make it engineered. Again, this cell can be implanted in the body, And in such case, this type of cell finds the cancer cell is a very ferocious way. So this is a very important way. It is a fundamental way to find the cancer cell from the body. And this promising treatment strategy actually approved by the FDA in 2017. So it is a very already effectively using such type of therapy style here now. And it is important, it is interesting. You can see one is the yellow one, and this is on the red one. This is the yellow and the red one. So here you can see how it works. The engineered T cell therapy, engineered T cell attacks when the leukemia cell. This red cell is the CAR cell. Red cell is the engineered T cell, and the yellow cell is the leukemia cell. So this in this way it can develop our immune system, and the cancer cell should be identified and killed by this immuno-engineered T cell. So this strategy can be applied by our doctors for the patient of the cancer patient for the treatment of the cancer. So now applying or introducing these two type of control. One control is EU1, we call this control the immunoboosting drugs, because some controls, some foods or some drugs increases our immune system. When the immune system is strong, so some viral disease can be prevented. And the other one is the CAR T cell therapy. That is the engineered T cell therapy. And then when we use this two type of control strategy, or immediately this model looks like the optimal control model in this way. So this is a very simple case when if you understand how we introduce the control in the system, and also this optimal control model also published is a very another good journal of Applied Mathematics and Competition. So now it is the formulation of the model, and then we go for our optimal control, how we can formulate in the optimal control way. So you can see we would like to minimize some objective function. So the objective function I actually the infected cell. So we should minimize the infected cell, and all the two controls should be minimized, because all the control have some cost, involve some cost. So all these should be minimized over time 0 to t, that is a finite time interval, and subject to the constant. This constant is the dynamic constant, these three differential equation with some initial condition. So this is a very simple case we can consider, we can apply, we can introduce in our dynamic model. So now I am going to very closely to finish this type of application in applying the numerical scenarios, because the theoretical validation already done. If you go in the paper, you will find all the details, theoretical validation of the theory of the paper, of the model, and then I am showing here a comparison of this theoretical of introducing of the control strategies. So when we introduce the control, you can see here without control and with control. That is, without control mean we don't use any immuno boosting drugs or engineered T cell therapy. We don't use anything. That's only our model describing this one. But you can see the red one is without control, and with control this the blue one. So here only we use only one control, that is not both together. We can use only the infected cell immunotherapy, but in the absence of immunoboosting drug. That is, here we don't use any immunoboosting drug, only use our engineered T cell therapy. But here we can use in absence of immunoboosting drug, but our immunocell is increasing. You can see immunocell is increasing in the red one, and not red one is the maroon one. This is the dash one. This is the immunoboosting cell, and immunocell is increasing very significant way. So now if you go further in the another one, this is the infected cell. is decreasing, and also the immunocell is increasing in a very significant way. When we use only one control strategies in our model, in the mathematical model. So now, when you use the both control, the variation looks like, again, the significant boosting, immunoboosting drugs, and as well as the engineered T cell therapy. In both cases, our immunocells and our immunoboosting immunocells and the infected cell. Immunocells is decreasing, and immunocell is increasing, and the infected cell is decreasing. So anyway, there is another application. I am going to very quickly just show the significant application of the state constraint. State constraint. Actually, this type of model is another immunotherapeutic model when we use in the HIV model. Here, the HIV model is also a very simple model. Only we consider two components. Only one is the virus, that is only the virus. Another is our healthy cell, that is the T cell. But here the control strategy looks like in the similar two. And one is the immunoboosting drugs, another is the immunosuppressing drugs. Immunoboosting drugs, another is immunosuppressing drugs. These two control combinedly give us the treatment strategy of the heart. You know, heart, what is heart? Heart is very important nowadays for the treatment of the HIV. Highly active antiretroviral therapy. So this type of heart treatment, actually, it is not the single drug treatment. It is at least more than 3 drugs combination. And more than 3 drugs gives actually a very significant results for the treatment of the HIV. So we consider here another model, but this model actually is considered first by Krishna and Webb into 1998. If you consider such type of model, you can find this Krishna model, HIV model. Krishna Webb, they are actually the microbiologists, but they know a lot of in mathematics and mathematical modeling. But here you can see they don't use any control strategy. This is actually the transmission or the internal interaction of the cell and virus. But when this model was developed using optimal control, this control should have two control strategy, U1 and U2. I already mentioned this. U1 is the immunoboosting drugs, and U2 actually the immunosuppressing drugs. Virus suppressing drugs, virus suppressing drug and the immunoboosting drugs. And this model was developed by Hemraj Joshi and using this control strategy. And the same is the objective function minimize and to control looks like this. All these control should have bounded in a measurable sets. But what is our development here? I developed this model using a state constant on the virus, because virus actually the state variable, but we don't want the virus should increase at unlimited way, because when virus is increasing, our cell goes to decrease, and in that case the patient is expected to lose his life expectancy for a longer period. So our main aim is to make the virus to keep at a certain level, minimum level. So we need to put the upper bound of the virus concentration of the virus cell, that is B less than equal B tilde. And introducing this type of model, we get our computational results. Just I am showing here very simple in a graph. You can see without control, CD cell is going down, virus cell is going up. But when you use the control, then CD cell is going up, and again the virus cell is going down. So this is actually when we need to know that treatment is very essential, and we need to verify, we need to introduce such type of drug for the solution. But when we apply the constraint on the virus cell, you can see the virus is going up. In the very beginning is going down, but again at the certain period, when the virus can be resistant, it is going up. But I put here, you can see the virus should go at a minimum level 2.5. After 2.5, it is not going up. It maintains at a certain level. It is not going up. Even it can be protected, the patient, from this type of virus cell increasing a tendency from the virus cell. If we put the hard treatment from the very beginning, or the multi-combination virus cell in a very good scheduling, then it is possible to these virus cell to lower a minimum level, because we consider the initial value only 2, and it is possible to maintain this virus in a minimum level. In that case, we should make the drug combination, that is the drug combination, highly active antiretroviral therapy should be used using a very expert physician, expert doctors. Then it is possible to cure the patient from the HIV, because there are at least 3 cases have been happened who have been cured, functionally cured from the HIV virus. So this is actually the research I am sharing here. I am not going more the details here. So thank you so much for attending and for listening my talk. And if you want to make any research collaboration, we can go further. You can find many details about in my website, and many several application of optimal control in different diversified areas. There are many other collaborators in different countries who are working in this area. Thank you so much. Thank you for your attention.
Good afternoon, sir.
Good afternoon.
Sir, can you suggest some book on optimal control? Actually, it seems very interesting to me.
Yeah, it is. You can find one book is very interesting. It is written by Susan Lenhart, Optimal Control Applied to Biological Models. It is a very good book, because there are many computational coding, that is in MATLAB code also there. And this book is written very simple English, so it can understand any students, any scholar, MSc, BSc, or PhD. It is very interesting. But
can you write in the chat box, please?
In chat box?
Yes, sir. It will be better for spelling or.
Okay, just I am finding the chat box. Where is the chat box?
Or you can say I can write, sir.
Okay, you can write optimal control applied to biological models. Optimal control applied to biological models. Susan Lenhart is an American professor, very nice, and this book is very simple. There are so many applications also in this book. But
okay,
state constant application is not so much there. If you want to go for the state constant problem, you can find many papers or my website or my thesis. You can find my thesis in my website as well.
Okay, sir. Okay, sir. I shall go for it, and probably I can mail you, sir.
Okay, thank you so much. No problem. You can mail me.
Sir, I shall find it in your website.
Yeah, my thesis is also in my website. If you go in my publication list of publication, if you go to the bottom, then you can find the thesis of my PhD, and there is a link. Just click on the link and you can find the thesis.
Okay, sir. I shall try to mail you.
Okay, thank you so much. Yeah.
Kumar sir, audio available? Okay, 10 minutes, Dr. Aman sir will join.
Yes, sir. Yes, sir. Very good afternoon, sir. I am very thankful to Dr. Krishna Padadas for inviting me such a great kind of opportunity to speak on a topic introduction to ArcMap. So, first of all, I was busy with some kind of schedule in a meeting with the university people. So, sorry for coming late. I mean, I have just prepared a few kind of things related to ArcGIS and ArcMap, right? So this is a kind of thing which is related to the software project which I have recently received from the DST. So a bit introduction to that, which will be probably helpful to you people in this uh, kind of expert talk. So very introduction, very good afternoon to all of the participant. My voice is audible to all of you. Okay, okay. Now focusing on to the main slide, which is related to the project that is ArcMap. So it is basically some kind of ArcGIS, which is the software available in the you can say Chat GPT. So what that kind of software available? So it contains basically uh, working on the malware analysis. I think you people are aware of the things malware, viruses, and another kind of things because these are the threats in these coming IT kind of things because we have to work on a lot on the things related to the viruses and anti kind of things. So we have to diagnose various kind of vulnerabilities related to ArcGIS. So ArcGIS is basically software when you are searching on Chat GPT. So what they will write that such kind of software has been stopped in 2022. Why so? Because they are working on the beta version of that. So with a short notice, I was able to arrange ArcMap, which is a map-centric GUI-based tool. And this special tool will help you to work geographically and also to interact with the various kind of maps. Supposedly a person is going from the A destination to the B, so definitely they will go for the Google map kind of thing now. So that is the application of ArcMap. Then there is one software which is next slide. After 15 minutes I will show the ArcGIS, which is working on such kind of vulnerability that how they are working on the synchronization of various maps for the destination like A to B, what kind of various threats and vulnerability can be occurred. So in this software, what is happening, we are creating the map by geographically and interactively, and to display the various export or to print or to publish. Here we have to edit the various kind of data that are maybe static or dynamic, and then we have to modify the features. A very interactive and very useful feature which I have observed in this software, that is query. You can also go for the various kind of queries related to the map optimizations, and very needful kind of thing, that is charts are available. For example, we are working on the Excel kind of sheets. We have to make the various kind of decision making with a short span of time. We are able to generate various kind of chart, like radar chart is there, and multiple kind of things which will help for the optimization of these mapping based technologies. And very last is reporting. It has the facility to print in a 2D and 3D form also. So next slide is giving you the analyze what we are having here. Why it is so much useful to view people, because such kind of maps will be able to visualize globally, not locally, even throughout the globe. You can visualize the information in form of patterns, hidden trends, and relationships. And we have to solve the problem. How we are solving the problems? In this software we have various components available. We are able to do programming using Python, so it is also Python enabled kind of thing. Next is both data editor as well as map generator is there. Yes, of course, it is providing you the both kind of facilities to you people, because when you're working with the global kind of things. It is giving you the facility to both edit as well as to visualize your maps. So it is not only map focused kind of thing. We can work on the Python based library. Now moving to next slide, I think it is visible to you people navigating around the map. So what this facility is available to you people. On the right hand side, we have the maps available with the tool, standard tool, drawing, utility, network analysis. So this is one of the visualization kind of things which is available to you people. And what other kind of things are not available in the previous era of this software like ArcGIS? They are not providing the utility network analysis. Then we have editor, in which we can edit the various kind of A to B destination and in between stations also. Let us suppose we are moving to Romania, right? Globally, we are moving to Romania map. What we are doing, from A to B, we have multiple kind of base station and destinations are available. So in between that, we have various kind of layout followed by its network analysis, and that will give you the right kind of view that where we want to move optimistically. So it is kind of self-generated kind of optimization. Then we have effects and layout. In layout, we have just 2D and 3D facilities available. In next slide, it is available. And in effects, we are having the special 2D and 3D. Supposing in MATLAB, we are having the 3D kind of graphs available. But yes, using ArcGIS or ArcMap, we are able to visualize the 3D map with the extra facilities of your network analysis, and you are able to go for the effects of the specialized part, right? For example, this is the next slide, Arc Info 8.0.1. So that is the demonstration map, which is giving you the frequent information about the various destinations. So in this case, we are just check boxing the metroplex area, countries, and Texas. So these are the global information available. So using this software, what is the beauty of this software? You are able to move from one place to another. In addition to that, we are also focusing on the standard layout as well as movement from one station to the another. Next, when we are unchecking the things, let us suppose Texas and Metro box is not there. So it will not visualize such kind of things. It will only focus on the Dallas country zip code. I have some video available with you people so that it should be very clear to you people that how this software is working and how it is fruitful to you people for moving from one place to another in addition to the Google map, right? So in this case, Arc Info 8, that is the latest version, which is working on the various layers. Let us suppose we are moving from A to B. We have some map extend and projections are available in the Google map. But somehow in some projection, these things are not geographically available because its persistent is not there. So its various sub layers are available in ArcGIS and ArcMap. And these layers support the thematic mapping, then single symbol values and unique values. So what new things are added as compared to the ArcGIS? The graduated color ramps, proportional symbols, and lookout tables, which were not available in its Google Map and ArcGIS, right? So that's why the lookup table and pie and bar charts maps are available. So what is inside this layer? So inside layer, we have the various kind of data references stored. So how these references are working, it is somewhat similar to the algorithms we are working on the location based of the stored references. So they have opened the spaces for doing research on the local as well as global maps. Then we have data location. We have to change from the one place to another because you are the data source for yourself also. And one secure thing is available that your things will not be persistent to anybody else when you're working on this software, right? So which is the add-on advantage as compared to Google Map. Next is the managing layers, how we can work on the various kind of layers and its management. We can change the layers of the test description, copy layer, remove layer, so which were not available in any kind of software till date. Then display layers on the different scales. Then data frames. So I'm again focusing data frames. Why data frame? Because data frames were also helping you to visualize 2D and 3D. In addition to that, to organize the layer. Let us suppose if layers are not available, you can add layers by yourself. But as a security point of view, your things will not be shared, because we are also get afraid of the things that for example kaggle.com is there, your data set is available to each and everyone, no? So when it is going to be open source and published to everywhere else, we have some security things that it should not be get into the copied kind of things. So that's why sub layers will not be get copied in this kind of software. And you are able to manage in this slide, we have some active data, active data and data frames are there. So we are working on multiple in a local as well as global kind of thing. We are working on the Texas, then Dallas and North Texas countries also. So these layer will be focusing on the on left hand side and bottom of the sides. Next slide is focusing on the map data sources. See, in this particular kind of software, we are having the Python library available. We are working on the TensorFlow. We are working on the geographical kind of database. So these Python-based data set is readily available, which is the right kind of thing in this software I have achieved. And we are able to get its destination. How it is possible? We are asserting just maps only. Means we have to just drag and drop the map of this USA and it's a particular portion, and we have to scale the bar and scale the text. So how it is helping to you people, it will be give you the some redundancy removal. When you're working on the Google Colab libraries or the Google Map, it has some kind of redundancy available. But when you are working on the Arc Map or ArcGIS, so this kind of redundancy has been removed. And we are able to label the data using these two things also, which is not yet available in your MATLAB also and another softwares. I think I will share the video. I will just share with the video. It is very some interesting kind of things are available. If it is.
Hello guys. Welcome to this beginner's guide to ArcGIS desktop tutorial. Through this tutorial, I aim to give you guys a very in-depth understanding of the capabilities of ArcGIS desktop if you're getting started as a beginner. Now, Esri's ArcGIS has been around for quite a long time, and even today, despite the competition it gets from so many other commercial and also open source GIS tools, it remains as one of the most widely used GIS softwares in so many different areas like the health sector, transportation and navigation.
So as I already discussed with you that Romania map is there. So these are just citing the things. I have fetched 1 or 2 videos to you people that you should be able to get such kind of frequent information within a fraction of second.
Water resources engineering, geological sciences, you name it. So yeah, before we start this program, let's just see what sort of topics we're going to cover during this tutorial. Now again, this is an introductory guide for beginners, but what's interesting is that I'm going to take you through these functionalities, which we're going to discuss through practical applications. That means by the end of this course, you will know exactly what can be done using the available tools, and also how you can use those tools to actually get the work done that's relevant to you quickly and efficiently. I have divided this tutorial into 4 parts. To start off, I'll give you a bit of an overview of what ArcGIS Desktop is, and we'll discuss the different components of the interface. Then we will move on to discuss how we can use this software to work with vector data. Now on the screen, you can see the type of subtopics we are going to discuss. Things like types of vector data, how to do basic styling and geoprocessing tasks, and how to edit the attributes, and how to use the field calculator and the geometry calculator, and how to digitize things, and how to create new shape files, and how you can export those new vector files into different file formats. Now in the third part, I will be going over how we can use this software to work with raster data. Now we will be covering things like introduction to raster data, styling and visualizing, how we can use geoprocessing tools to work with raster data for the purposes such as clipping, and how we can actually do a 3D visualization of a raster, discuss things like what is raster reclassification and how to get certain spatial statistics from raster data. Also, I'll be showing you how we can convert between rasters and vectors, and what could be those potential benefits of being able to convert between raster data and vector data. And in the fourth part, I'm going to explain to you guys how you can create a standard map using the data which we worked with to create a very meaningful map which you can, let's say, present to your clients, or even just do it for yourself for your own satisfaction. Now, as you saw, we are going to cover quite a bit of things here in this tutorial, and I will guarantee that this will be sufficient for you to have a general understanding of the capabilities of this software. And then, of course, with that head start, you'll be able to easily discover a lot more on your own quite comfortably. Alright guys, so without further ado, let's go ahead and get started with the tutorial. ArcGIS Desktop is comprised of 4 main parts. We have ArcMap, ArcCatalog, ArcScene, and ArcGlobe. We can say that ArcMap is the primary application where we usually put most of our attention, because that's the program which actually lets you work with our GIS datasets to do things like use the geoprocessing tools, compile and edit the GIS datasets,
So this is what I want to share to you people. Even I will share this slide because this is very much beneficial. These 4 kind of things are available on a single platform, ArcGIS Desktop. And how it is beneficial to you people, because you are able to do many activity parallelly. And one more video is there, what that is showing. Hello, to viewers, you. Have a good day. Welcome to another tutorial. So this is available with my channel, and I will share you. Work with ArcGIS. So this is the first tutorial of that series. ArcGIS according to our, you can say, the best way. By that we can. So this is all kind of only elaboration of ArcMap. So it has contained into the 4 different utility parallelly. So this second slide will give you somewhat over file, edit, view, etc. And after that, you can see at the shortcut menus. Okay, so basically we actually doing all activities in ArcGIS by using the shortcut menus. But the most important, or you can say the most important, is the tool of ArcGIS within this. This is the table of content, catalog, search, and the Arc toolbar. This 4 is you can say more the main pillar of ArcGIS. So we should arrange this 4 pillar.
Okay, so at first I want to click on this table of content. So you can see if we simply click here, we can see here this table of content, and this table of content always should be within this left portion of our ArcGIS. Okay. Second, you can see here this catalog. Simply click here the catalog. So you can see here within this table of content, within here catalog as well as table of content. So when we click on table of content, you can see here table of content as well as the catalog. You can see a table of catalog. So we can see here within this catalog, we can see the folder. Okay. So when we navigate the folder, we should.
This is very basic kind of thing to create the folder, but after that some new kind of things which is I think not I mean listen by you people, that is beneficial to you people, that how ArcMap is beneficial to you people in this in context to optimization.
And the table of content means all the activities or layers will be available here, and I will show after a few minutes. Okay. Then you can open see here the third on the search option. This is also very much important. Simply click here. You can see search option. Okay. So then within this search button, we can easily type anything. So whatever we need, we can type here. We can easily find that, and I will show that also. And the most important thing is that our toolbox. This is the, you can say, main backbone of this, you can say, the ArcGIS. So all these activities actually we're doing with this ArcGIS basically based or work within this Arc toolbox. And Arc toolbox has 7 wings, and each wing, or you can say the section, has a different work. But basically we use the spatial analysis tool. Then you can see here the data management tool, then conversion tool, and the third one is the analysis tool. So these are the main powerful tools that you actually use different kind of work with ArcGIS. Okay. So after that, you can see how the left and right portion is okay. And rather, I want to show it here. You can see at the very left portion. Okay, 2 small boxes you can see here. So the first box, when I cursor point is set here, you can see the data view. Okay, that means the all layers, that means point, line, polygon, or raster vector data, we can see within this, you can say data view. But the second, you can say, is simple small box, when cursor point is set over here, you can see the layout view. So if we click here, we can see the layout. So this is actually the point. Actually, this is the shortcut menu that we use for the final layout. Okay, so all of this we'll learn step by step. So again, I want to click on this data view. So this is the data view. Now you can see here only some very few, you can see symbol is here. But we need to add some more symbol to work, you can say, very precisely and very fastly. So most important tools, or you can say shortcut menus, that we have to add here. These are, you can say, drawing tools, classification tools, georeferencing tools, editor tools, effect tools, and the tools only. So one by one I will open it. So for that, firstly, you just click on over here within this any portion over here, right click. Okay, and we can see here different tools name here. Okay, so you can say one by one from the upper portion to lower portion. You can see here. First one is important. The very much important one is that from this is the editor. So simply click on the editor. You can see an editor tool already open. So you can simply left click on your mouse and you can drag it here. And you can set anywhere according to your suitable position. Okay, you can set this. So this is the editor. So all kind of editing. That means the point, line, polygon, whatever we digitize, we'll use this editor toolbox. Okay. Secondly, again click on right click and you can select the effect. This effect tool is also very important. You can say in during this the classification, supervised and unsupervised classification, another thing. Again right click and I can select here georeferencing tool. Okay, so where is georeferencing? Yes, so this is the georeferencing. So this is very much important because when we have a raster map without the you can say georeference, so you need to georeference map by using of this tool. So I want to set this georeferencing tool here. Okay, and you can arrange all of this tool according to your need. Third one is the important, you can say the drawing table also. So you can see here the draw. Okay, click here. So you can see here the drawing table also available here. So I want to the drawing table adjust here. Then I want to add the classification table. So you can go here, the image classification, and you can also see here some other tools also is available here. So I can also take this tools.
So these are the options to add and which is not available in any kind of tool.
Tools here. Okay. So tool table also very much important. Effect type already added, editor toolbox already added, geofencing tool already added, then the classification tools. So that you can see image classification tools. You can see here. So I can also simply take it here. So these are the, you can say, the basic tools or very essential tools for, you can say, the doing any kind of the mathematics. But if you have need more tools, you can simply click here and you can check, or you can say select any tools from here. Okay. Similarly, you can also find all of this from this. You can say the customize, go to toolbox, and you can find all of this here also. Okay. So these are the, you can say, basically think about the you can say the basic symbol. So here you can see another important and strong, you can say, tool is the window tool. So here you can use the image analysis tool. So image analysis tool is also very much effective during this all kind of, you can say, the satellite image, whatever this Landsat or you can say lease or spot or others. So this image analysis tool actually used during the, you can say, the image analysis or classification. So that we'll learn in later. Okay, so these are the basic thing about the, you can say, the settings about the ArcGIS. Now we'll learn how to open raster image, how to open the vector image. That we'll learn in this topic because these are the very basic things. Okay. So for the opening of the open raster and open vector layers, you should go to the catalog. You can see here catalog. Within this catalog, you can see here the folder connection. This folder connection is very much essential. Okay? With the help of this folder connection, we can directly, you can say, the navigate the folder where my vector as well as the raster data available. So I should connect. So simply click on here, folder connection, click on the connect folder. Okay. So after the clicking, you can see here new window will appear. So from here, you should select this folder where your vector as well as the raster data is available. So my vector and raster data available within this, I think this Landsat. Okay, within this. So I want to select this Landsat and click on OK. So you can see here within this folder connection that folder automatically connected. And then you can also see a plus icon. If you click here, you can see the folder which is within this Landsat that also appear here. And again, if I click on this data, because my all Landsat image actually stored within this data, if I click here within this plus icon, we can see the other folder. We can also extend this. That means all of this folder you can see here. So you can see here the area boundary, in the district shapefile, in the state shapefile. This is the folder where the different vector as well as raster data is available. So at first I want to open the raster data. So that raster data means the satellite image. You can see here different satellite image here. Landsat 8, Landsat 7, Landsat 5. Okay. So at first I want to open the Landsat 8 satellite. Okay. Very simple. Simply click here. You can see here within this, there's a number of satellite, you can say satellite images here. So for example, I want to show something that I want to select only one. So select first one, you can say select one. Okay. And after that, just drag it. Okay. Select, simply press right click on this Landsat 1. Okay. And drag it here. So So you can see here that band set 1, that is Lancet 8, band 1 appear within your map. Okay, but we can also open all these, you can say the band 1 to band 11 or whatever you need. You can also open by clicking other way. You can also see here within the standard toolbar. Okay, so this is the standard toolbar. This is the standard toolbar. Okay, so with the help of this standard toolbar, okay, I want to set again standard toolbar here. You can see a plus icon. So this is the add data. This is directly add data. Okay, you can simply click here and simply again navigate to the location where the data is available. So our data is available within this Lancet, this data, and this first one, the Lancet 8. So we can see here the all band is available here. Okay, so I have to select band 1, then band 2, 3, 4, 5. So I have to select only this 5 band. Okay, then click on add. So all data, all band will, you can say, added here. So how we can see that all, you can say the band are, you can say, yeah, appear or not. Okay, so you can click here, table of content. So simply click here, table of content, and you can see here all band. You can also extend this one. Band 1, band 2, band 3, band 4, band 5. And band 1 also. Previously, we actually opened this band 1, so I want to remove this. So if I want to remove any band from this table of content, you can easily remove. How we can remove any band or any layers from the table of content? Simply just click here, right click, and click on remove. So band will remove from here. Not only that, other thing is that you can see here the on checkbox for each band. So if I uncheck, so we can see all band are individual band will disappear. So if I want to see only band 3, so you simply click on this checkbox. So on the band 3, that means band 3 is a green band. So only green band will appear here. So if I want to see only the band 4, you can see only band 4. If you want to band 5, so you can see here only band 5 only. Okay, band 5 is a near infrared band. You can see here. Okay, so this all about the layers, opening of raster image. Okay, so now I want to open only, select only this band 1. I want to share something. If I want to, you can say move my band, or you can say my raster image from here to there. So in that case, I will use this pen, because by using this pen, we can easily move. Okay, we can easily move our raster image anywhere, whatever you want to move. Okay, so simply this. And this is the plus icon, which is the zoom. So if I want to zoom this portion, so you simply click here, and you can see on the zoom portion will appear. If again I can zoom it, and this actually used for the zoom out. Okay, so zoom in and zoom out. We can also, you can say, zoom in and zoom out by the help of the mouse button also. Okay. The second thing is that you can see at the full extent. This is the shortcut menu. You can see here my raster image actually spread over the image, so over the area. So if you can say if you want to see within this the layer within this window, so simply you can click here full extent. So you can see here all map within this your window. Otherwise, you can also do like that. Select this layer, this band 1. Simply click on right click, and you can see here zoom to layer. Simply click here zoom to layer. So your map again will fit with the you can say the display. Okay. Second, you can also see here zoom, fixed zoom and zoom out. You can also click here. So fixed rate wise, your image will be zoom in as well as the zoom out. Okay. And also you can see here zoom in and zoom out. Okay. So these are the basic thing. By using that, we can easily do so many things. Okay. So now you can also see here, this is the select element. So by using that, we can see, we can only select, but we are able to move. If we want to move, and you can say the image, we have to select this tab. So by that we can move anything within our, you can say layer, within our window. Okay. So about, you can say here this is the zoom to layer. Okay, so here you can say the basic, the about the concept about the opening of the raster image. Here I want to see one thing, one important work within this window menu. Simply click on window, then click on image analysis. So you can see here 1, 2, 3, 4, 5, 6 band.
This is very important.
If you want to merge all of this band, if you want to see in band as a, you can say the false color composition, then what we can do? Simply select all of this band within this, you can say, image analysis. Then simply click here within this here. You can see here. This is the merge. Okay. This is within this processing. This is the merge composite band. Simply click here. Okay. So we can see here within this layer panel, the composite band will appear. So what we can do? We can easily click on this minus button, and I want to uncheck all the band. Okay. So you can see on this composite band, and within this composite band, you can see here red, green, and blue, because all 5 band actually merge within this one band. If I want to see this image as a red, you can say the false color composition, then click here, select band 5, band 4, and band 3. So this is the false color composition. Okay, so you can see here the all our yellow portion is the vegetation cover, and the blue color is the river, and the green, you can say the yellowish color is the vegetation, sorry, the agricultural land and other activities, and the bluish green actually represent the settlement areas, or you can say built up areas. So all of this you will learn step by step with me. Okay, so now I want to remove all this layer.
So this is a small kind of thing which is readily available on some kind of channels also. Even I will share my PPT to Professor Krishna Paradas for the same, and with a short span of time I was able to share this PPT, because I was expecting it was on 7 to onward. So I was driving, so I am very thankful to again Krishna Paradas for the same. Any kind of query you want to ask? Okay. Thank you very much. Oh, thank you very much, sir. Thank you.